Sticking with the monkey for now. Not directly, but I collaborate on stuff, so.
Yeah, okay, nice.
I assume you're going to stay for the full time.
Wait, how come it says 9:05 now? When did that happen?
There seems to be two versions of this schedule. One starts at 9:01 and 9:05. Yes, I was. We chatted about a few things. And we did. Very early, yeah. Yes, I mean, I think they might have consideration to step So David's apartment only existed for a relatively short period, and those of us who were like part of that feel like family in a way. We have this like connection, having like that's this new thing, and it has like a show, it's a specific lifetime, and so yeah, I feel pretty close to the other. I mean, the institute is still there, but it's used. And so like in the middle of the pandemic, they would announce it. And that's how, I mean, that's the thing how it works. I was doing stuff very unrelated to what he does. He brought me in because I actually I studied it, so he was like, great. Yeah, and he kind of let me do it all. But, again, like in the middle of the pandemic, moving to Israel. And it was kind of definitely a big, like, kind of like, okay, you know, and so like, it was kind of, like I said, this very family feel, but like, people, there's a lot of emotion. Yeah, I think there's a chance I might still be in a group phone chat.
Morning, everybody. Welcome to day 3. This morning we're going to have 2 sessions this morning. First session has 3 talks in it. We're going to have Matthias Gruber, Yifat Levy, and then Angela Yu. Same things as before. The talk's going to be about 20 minutes. And then afterwards, if you have questions, please stand up, line up at the microphones. We'll alternate between them. We'll just take it away from here. So, Matthias, can you get to your slides?
No, I think Hector is doing that. I think Hector is in the room over there. We would need the first slides, please. I can't do anything here.
So there's no, this isn't a touch screen then?
I don't think so.
As I'm tapping on it, it's not doing anything. There we go. There's Matthias. And okay, slide go.
Perfect. Thank you very much. Thank you to Jackie and the whole team for organizing this really great event. Thank you for all the inspiring presentations so far, posters and talks. I found it really inspiring, which is really great news. But also this comes with bad news for you, because I was so stimulated by all your talks that I couldn't really decide what to put in my talk and what to focus on. So instead of just presenting 2 key studies, carefully running you through it, I will present kind of like a little tour of what we are working on in the lab. So brace yourself, take a sip of coffee, and take a deep breath. So I'm originally coming from the memory research area, and I was always fascinated that curiosity is seen as a fundamental aspect of learning. But the influence of curiosity in learning is really poorly understood. And as a memory researcher, as I started to think about curiosity, I was quite fascinated to come across a chapter in this really landmark book, like it's really the Bible for everybody who studies the hippocampus. The hippocampus is a cognitive map written by Nobel laureate John O'Keefe and Linda Dell in 1978, where they dedicated a whole chapter on exploration and how exploration affects cognitive map formation. And there are several really cool quotes in there. For example, cognitive maps are built not to satisfy biological needs which the animal currently entertains, but on the basis of curiosity, the motivation to know an environment, to know where one is. And also they speculate much more about it, that this preference in animals for going for novel stimuli compared to familiar stimuli, that this reflects the preference of curiosity over anxiety. So when we started this work about 10 years ago now, with our first fMRI study, we showed in the trivia paradigm, we'll go over the details in a minute, that curiosity states affect the dopaminergic circuit. So here you can see the 2 key regions within the dopaminergic circuit, the SNVTA and the nucleus accumbens, and you can see activity in these 2 regions ramps up the more curious a participant is. And this is really nicely in line with what we think the dopaminergic circuit is doing, that it really supports exploration and information seeking, really that drive to get new information or to get a reward. And then we further showed that this also interacts with the hippocampus. So interactions between the dopaminergic circuit and the hippocampus support the curiosity-based learning enhancements. And then we took a step back a little bit and thought like, well, let's think about it more from a neuroscience perspective, and let's try to integrate these early ideas, for example, from Daniel Berline and George Lowenstein around curiosity, and see how this could map on to the neural mechanisms related to curiosity. And when we worked on this paper in 2018, it was published in 2019, there were just a handful of fMRI studies out there. So we tried to make sense a little bit and started with a very simple model. So this framework basically lays out like multiple events at different levels of analysis. So the key question is then, and we talked about that already in the last days, what are the elicitors of curiosity? And just to do a quick run through, we think that this is basically dependent on two key areas, or two key hubs in the brain with the networks involved. On the one side, the hippocampus and the anterior cingulate cortex. And they both are involved in coding prediction errors. The hippocampus more related to context-based prediction errors. So this is really in line with the ideas from John O'Keefe and Lynn Nadell, that the hippocampus is really this mismatch detector, right? That detects novelty in the environment. And the ACC as a detection of an information gap due to cognitive conflict. But of course, as we have heard, the ACC is doing so much more in terms of metacognition and controlling metacognitive processes. But then we have this thing in between, like this appraisal component, because we think it's like not automatically, as John O'Keefe and Nadell also pointed out, that this basically a prediction error leads to curiosity. There has to be some evaluation in there based on the context, based off the cognitive resources that an individual has. So really appraising the information, whether you have the coping strategies to deal with the new information. And if you think you have the coping strategies and you're in the right context to deal with it, then curiosity is elicited in some degree. But on the other side, if you can't basically tolerate the uncertainty, or like if you can't tolerate the novel response, then this will lead to anxiety. It might be more threat-inducing response. And as we heard yesterday, this leads to a different neural mechanism, more related to amygdala and hippocampus-dependent functions. And then basically when curiosity is elicited, and curiosity could be satisfied or not, this could actually lead to another prediction errors, and the loop basically starts all over again. So in my talk, I will now focus on three things in terms of individual differences in curiosity. First, the effect on learning. Second, the individual differences in curiosity and the effect of information seeking. And then the third one on exploration. So let's start with the first one, individual differences in curiosity-enhanced memory. This project has been led by Katrin Eschmann, senior postdoc in my lab, who also presented a poster on the first day of the conference. So what we did here, we pulled together data from the lab where we had a trivia paradigm that was tested in the lab behaviorally, and also a separate 10-minute resting state fMRI scan that was recorded on a completely different day. If you haven't heard about the trivia paradigm before, probably most of you have, but in case not, let me walk you quickly through it. So we always start the trivia paradigm with the screening phase, where we have a set of trivia questions that are randomly selected, and we present these to our participants, and they give confidence ratings, how certain they are that they know the answer to the question, and a curiosity rating. The goal of that screening phase is that we have enough high and low curiosity trivia questions to present later on in the experiment. If somebody says they know the information to answer, giving a 6 rating, we won't take this question any further, because we really want to only use the trivia questions where participants don't know the answer. And I should also say, if you control later on in all the analysis in terms of behavior for confidence rating, for prior knowledge, you still see the effects of curiosity on memory. So it seems to be curiosity is a separate effect. And then in the encoding phase, we show a selected number of these trivia questions again. For example, what Beatles single lasted longest on the charts? Participants think what the potential answer could be, and at the end, we show the answer. Any guesses what the answer could be? So we probably have people in the room now with very high curiosity. Maybe they looked up already on their phone what the answer could be. Other people might show very low curiosity. Any guesses? I know it's early in the morning. Hey Jude. But then also, you could be very much surprised by this answer. Like, really? It's Hey Jude? It's not yesterday? And you could think like, oh, why was that? When was that? What album was that? So this actually then could increase your interest actually in this answer, right? So we get now in our newer studies this interesting rating. And what we do with this interest rating, we compare that to the previous curiosity rating. And this approach has been developed here in Daphne Shohami's lab. So we just take the difference between post-answer interest minus pre-answer curiosity, and we call this an information prediction error, or an IPE. So this IPE really reflects how much more interesting the information was than you actually thought it would be. So let's look what we find in terms of the behavior, and this is basically we replicate what's been found previously in the literature. It's a quite stable effect of curiosity, how it enhances memory, but you can see there's lots of individual variability in here. And also we show again this IPE, prediction error related memory enhancements. It's mostly driven by positive prediction errors. You can see this memory improvement here. And now we ask the question, well, let's put the PACE framework to a test, and let's see if we only look at the connections within the PACE framework that might be important for curiosity and prediction errors. Is there any meaningful connections in there that would predict the individual differences in these two behavioral memory benefits? So, and what we found basically is, the first one is, we find a double dissociation. The first one is all about curiosity-related memory, within the dopaminergic circuit. So what we show here is, or what we found is, that functional connectivity at rest between the VTA and the nucleus accumbens scales with the magnitude of the curiosity-related memory enhancement. And if we look at IPE-related memory enhancement, where you also could think like, well, the dopaminergic circuit could be involved, we don't find any correlation there at all. But then what we see, if we look closer at the IPE-related memory, we see a strong connectivity, again at rest, between the ACC and the hippocampus, predicting the prediction error-related memory enhancements. So it's a really clear double dissociation that we find here. We can control for overall memory performance, separate, are independent of each other. So going back to the PACE framework, you can see already that we might need to modify our framework a little bit. What we found is basically curiosity-related memory benefits in terms of individual differences are related to the strength of functional connections within the dopaminergic circuit, and prediction errors, the two key areas that we thought like the code prediction errors, they by themselves can already support memory enhancement due to prediction errors. So the second question now is about information seeking. How do individual differences in curiosity affect real-life information seeking? There, we basically ran a study during the COVID-19 pandemic. And just to highlight again, this is now in the middle of the PACE framework, where we so often think actually, oh, when we look at exploration and information seeking, especially in animal studies, that this is a marker of curiosity. But actually there's very little research actually that really looks at the link whether curiosity affects information seeking and exploration, because you could see that, you could imagine that there are other factors that drive information seeking and exploration. So in the next studies, we basically look very closely at this link, whether curiosity is really a driver of information seeking and exploration. So in this study here that we conducted during the COVID-19 pandemic early on, we re-invited participants back for an online questionnaire where we had already the resting state fMRI data recorded way before the pandemic, and also had curiosity questionnaires. And what we found here is that curiosity trait measured with the 5-dimensional curiosity scale by Kashtan, correlated with the frequency of information seeking around COVID-19 related news. I should mention it's all driven basically by the frequency. We had other measures about the detail, the duration, and the diversity of information. There we didn't find any correlation. It's really driven between curiosity and the frequency. And then also, if you look at the brain functional connectivity, again, if we look at the dopaminergic circuit, we found that functional connectivity, again, addressed between the VTA and the nucleus accumbens, also predicted the frequency of real-life information seeking. So you can see this as an index that actually, yeah, the curiosity system, curiosity traits really affects real-life information seeking. And this is supported by dopaminergic circuit functional connections. So now let's look at the last point, the role of exploration and how individual differences in curiosity affect exploration. So the first part, and we'll show 2 experiments on exploration and memory and curiosity. The first one was led by Angus Inkster, former postdoc in my lab. So here we had the idea, well, we have the trivia paradigm to look at curiosity. It's actually quite controlled and quite a passive paradigm, not really how curiosity works in the real world, but it works for our purposes to do it in the lab and to study the effects of curiosity on memory. Let's just now try an exploration game where participants explore a world, and in this game, the player is basically a nature photographer and explores these fantasy islands and takes pictures, different photos of the different creatures and plants that they encounter. So let's just see, like in this very uncontrolled environment, could we pull out anything there where we see that curiosity in such an uncontrolled environment affects learning and memory? So we tried to keep that as consistent as possible to the trivia paradigm. We used a screening phase where we showed participants all the different objects, creatures, plants that they could encounter and interact with in the video game, and got curiosity ratings on there, on these items. And then the second one, instead of a learning phase in the trivia paradigm, participants just played 30 minutes of the game, like one level in one particular environment. And also what we added there was a think out loud approach, where we asked participants really to verbalize how interesting they found actually all the things that they encountered. So we used this interest, basically think out loud approach, to again look at prediction errors. So we kind of like instructed them to tell us like, oh, how much did you like then when you actually saw this particular creature, or was it surprising to interact with it, or was it actually disappointing because it didn't do anything, and so on. So we tried to put a metric on that and to get to the information prediction errors again. And what we found in terms of behavior, first of the curiosity effect on memory, we didn't find a very clear memory benefit across all participants, as we usually do in the trivia paradigm, but we found that this was related to individual differences in terms of curiosity traits again, especially when we looked again at the Kashtan's 5-dimensional curiosity scale. It was related to joyous exploration. So what's plotted here is the level of joyous exploration per participant. Every dot is one participant, plotted against the curiosity-related memory benefit. So you can see that people who are more explorers, who are higher on curiosity traits, these are the people who benefit basically, where their memory benefits from a curiosity state. So in a way, this replicates quite nicely, more driven by individual differences, but it replicates quite nicely what we usually see in that more tightly controlled trivia paradigm. And also, in terms of the think out loud approach, I was a bit blown away that this actually worked. We also found that positive prediction errors affected memory performance in a positive way. So you can see the items that came with a positive prediction error much more interesting that participants actually thought they would be. They show a memory boost. So then the last experiment I want to show is about curiosity and spatial exploration. I think it touches on a few things that we've heard over the last 2 days. So here again, we create Dan Lu Chen, former postdoc and now collaborator, basically conducted and developed this virtual reality environment where participants have the chance to explore different rooms. And in this experiment, you can see that participants start a trial with a label of the room, so they know, okay, I'm walking up there to a lounge. We get again a curiosity rating. How curious are you to explore this room? They go up to the room, and then they have unlimited time, or not like about a minute, to explore this room. And then at the end again, we ask them again, how interesting was that room actually for you? And what we did here now, we were looking at the search pattern, or like not at the level of roaming entropy, this concept was introduced already yesterday by Catherine Hartley. So we looked at roaming entropy in terms of space, how much participants covered in a room. And also we looked at head direction roaming entropy. So you could imagine also like looking around basically in the room. So with horizontal head orientation and also with vertical head orientation. So you could see now different examples from the different participants here in terms of their roaming entropy measures. So for example, you can see this participant here walks around everywhere and basically has a high value of path roaming entropy, is also looking around quite a lot in terms of, in terms of visual exploration. You can see other indices, basically other examples here. So the question was then, the key question would be, is curiosity a predictor, a pre-room curiosity from the rating? Is that a predictor of spatial exploration? And indeed it is. So when we look first at path roaming entropy as a marker of spatial exploration, we see a positive correlation here. So the different lines are all participants. We have 29 participants, and overall you see when participants report to be more curious about an environment, they really explore this environment more. But in terms of post-room interest, we found something different. So again, we find here a double dissociation between these pre-information states and post-information states. The post-room interest rating is predicted by the head direction roaming entropy, so by visual exploration. So you can think of basically if somebody was very curious about the room, they walk around a lot, lots of spatial exploration, but if something maybe unexpected happens in the room or the room is particularly interesting, they basically actually stand and look around more. It's all part of the visual system, or like, visual exploration. And we just followed that up now in a larger experiment with more participants, where we now have 60 participants to also look at individual differences. I just put this slide in there last night, so it's a slightly different scale, but we replicate these findings, this double dissociation. The pre-room curiosity is driven by roaming entropy in terms of spatial exploration, and basic post-room interest again with visual exploration. And also in this experiment now we have a memory test, like a free recall memory test at the end of the experiment, where people really like just write down everything they can remember from these rooms. And we want to code that in terms of the episodic details that they remember. And also we basically let them draw basically all the different rooms. So again, that we can see the richness of how much they actually remember about the spatial layout. And then we also show them videos again of the rooms, how they explored them, and let them basically verbalize what they did in the specific phases of the different rooms. I think that's quite powerful to see, because we get a lot of course, lots of descriptions, what they see, but there's a lot of other indices of curiosity actually in there, where people say like, oh, I wanted to walk over there because I wanted to see whether I can walk up this room or whether I can open this chest of drawers and so on. So we're just trying to label all these different factors basically during these exploration phases. And to close my talk with, because this is the session really about individual differences, and we also looked again at individual differences. And the key thing here is like whether there's any mediator of the pre-room curiosity on the spatial exploration. And when we use again Kashtan's 5-dimensional curiosity, what comes out significantly is actually stress tolerance. This took us a little bit of surprise. We thought it would be again related to joyous exploration. I can see Jackie now like being fascinated because she has like just done Yeah, exactly. So it was great to see the poster yesterday, that this matches really nicely up. So to wrap up my talk, basically, I hope I could convince you that the PACE framework might provide a nice starting point to further structure and to stimulate new research on curiosity and curiosity-enhanced memory. I basically showed you how different functional connections within the PACE framework predict memory enhancements due to curiosity and prediction errors. We zoomed in a little bit more, actually, how curiosity and exploration how curiosity actually affects exploration and information seeking. And maybe that last data point about stress tolerance might actually be related to the appraisal process. Maybe this appraisal process shouldn't sit up there, basically, because curiosity was elicited and could be more of a mediator between curiosity and exploration. But this is now ongoing and future work in the lab. We are trying to now open this more like this black box about appraisal and evaluation of information and how that leads to curiosity or in some extreme forms to anxiety. So thank you very much for your attention, and thank you for all the people who actually did this work and my funders. Thank you very much.
We have a few minutes for questions, about 6.
Hi, Matthias. This is a really beautiful talk.
Thank you.
So I have a couple questions, but maybe I'll just start with one which is related to your last study. And my question is whether the memory sort of measurements at the end, like drawing, for example, are more related to the initial curiosity and the exploration, or actually more reflective of the visual looking and interest?
Yeah, so we haven't looked at it at all, so I can't really answer your question. But yeah, the key question is basically we want to know what is actually then the driver of the memory performance. Is it actually curiosity, or is it actually the exploration? So that curiosity is actually just the starting point. What curiosity leads to, that's basically having the effect on memory. Yeah. But yeah, really great question to tease that apart, whether this is, to control for that it is not just looking, and that it's, exactly. Thank you.
Very cool data. So first a clarification question, then potentially 2 follow-ups. When you describe information prediction error, that's signed, so meaning it's how much more interesting.
Mm-hmm.
So one question I had is, have you looked explicitly at whether the curiosity during encoding, have you asked them instead kind of how much positive prediction error do you expect, like the equivalent of that in interest? And is there a relationship between those? And then the other part of the question is, have you, and it might require kind of tweaking of the kind of trivia paradigm, have you been able to look at something like disappointment, like kind of like, if it's something substantially less interesting than you expected, and I wonder if you'd expect some kind of memory enhancement from like that kind of unsigned prediction error.
Yeah, so to answer the second part of your question, I think it's no, we haven't looked at that specifically. I think we would need to probably work on our stimulus set. So far, we were just interested in basically getting a stimulus set that elicits different levels of curiosity. So I think we would need to play around more with the answers to actually have more questions in there where the answer could be quite disappointing. For example, to look at that more specifically. I don't think we have a lot of that in our pool. And the first question was, I think, about whether we, instead of having an interest rating, actually to ask them directly, right? Like how surprising the information was.
Whether maybe instead of or in parallel with asking about curiosity, you ask them like how much more how kind of substantial do you think what's the range of kind of interest prediction error? I mean, ask in some way that makes sense to participant, but
yeah,
if that makes sense.
Okay, I need to think about that. Yeah, no, we haven't done that at all. Yeah, cool. Thanks.
Hi, Matthias. This is Kalina Christoph, UBC. Great talk, and I really like your model. Question for you that relates to also the last finding about stress tolerance. This part of your model that talks about appraisal and now links it to the lateral prefrontal cortex. I'm just curious to what extent it might be helpful to consider broadening the localization of mechanisms of appraisal to regions beyond the lateral prefrontal cortex, in particular if, as you related to the subjective perception of ability to cope with stress, which is a form of appraisal that seems to me that may have some conscious components, but I think there might be also a lot of subcortical non-conscious ways in which we actually estimate that. Just as a random example, I know people who go on SSRIs, which modulate the serotonergic function of the brain, often experience the ability to cope with stress. They just feel it. They don't think that they're capable of that. There's a lot of, so there's got to be some low-level appraisal mechanisms that give us that sense. I'm just curious to what extent it might be helpful in terms of accounting for some of the findings that you're seeing with stress capability to cope with it.
Yeah, I totally agree with everything you said. I think the approach that we took in this framework is like starting very simple as possible, and the appraisal component just captures like this cognitive control process, right? That there needs to be some mediator in there. But I completely agree, it's not just like these few regions, and it's more like the networks surrounding them.
Yeah, it could be interesting to broaden it also because it will be more integrally, it will help more relate structures like the hippocampus and the amygdala to everything else that's going on. Because right now there's a lot, but that's really interesting.
And it's also like most studies so far haven't been designed to look at that component. So it's really still a very black box. We don't really know anything about it. Yeah.
Thanks.
Thank you.
So I'm gonna have to cut off before the last two questions. Thank you. You can ask during the break, and there's also gonna be discussion time later. I want to keep us on time this morning, so we'll move on to feedback and our individual differences.
Thank you, Jackie, and the other organizers for putting together this really wonderful conference. I've learned a lot so far. And I think everybody in this room probably agrees that uncertainty has an important role in curiosity, creativity, and complexity. And as you know, there are huge differences and individual differences to uncertainty, right? Some people prefer to avoid it at all costs, whereas others embrace uncertainty and are willing to take a lot of risks. And so understanding these individual differences may be important in order to understand processes of curiosity and creativity. And perhaps the simplest form of uncertainty is what economists call risk, which is this, basically an uncertain situation where the probabilities of different outcomes are completely known. So you can characterize individual differences to risk in the lab by having subjects make a series of choices like these ones. And this is just an example from one of our studies to show that there is a lot of variability in the individual attitudes. Although there are commonalities, so most people are averse to risk in the gain domains and seek risk in the domains of losses, there are a lot of individual differences in these tendencies. And these individual differences may be saying something fundamental about us because, for example, there is evidence from our group and other groups of links between individual differences in risk attitude and structural features of the brain. For example, that includes posterior parietal cortex, the amygdala, and the cerebellum. But of course, the real world is more complicated. Usually we don't know the precise probabilities for different outcomes. And so a lot of studies also look at ambiguity when precise probabilities of outcomes are not known. And you can reach that in the lab by, for example, hiding some of the information about outcome probabilities. And again, you can characterize individual differences in the lab by having subjects make a series of choices. And this is just a random data set from our lab to show that there isn't a strong correlation between risk and ambiguity attitudes across people. Sometimes studies show no correlation at all, sometimes weak correlations. And so if you want to really understand individual attitudes to uncertainty, you should also look at ambiguity, not just risk. And it seems that ambiguity attitudes specifically may play an interesting role in psychopathology. For example, we've shown increased ambiguity aversion in the domain of gains in OCD, increased ambiguity aversion in the loss domain in PTSD. Others have shown reduced ambiguity aversion in several disorders. And there are a couple of really interesting papers from the lab of Paul Glimcher from recent years. This one shows transient reductions in ambiguity aversions in opiate users that predict subsequent relapse in use. So these were opiate users seeking treatment, and they repeatedly did the risk and ambiguity task, and these transient changes predicted changes in real-life behavior. This is another study showing that greater lifetime stressor exposure is associated with increased ambiguity aversion. And in a recent study from our lab, former graduate student Ronan Gia replicated the results for PTSD, basically showing reduction or increase in ambiguity aversion as a function of PTSD symptoms. So here, ambiguity attitude is depicted. Positive numbers indicate ambiguity seeking, negative numbers indicate aversion, and this is in the domain of losses. And this was replicated in a group of combat veterans. So all of them experienced some kind of trauma, but some developed symptoms and some didn't. And it was done in an MRI experiment. So Ronan was interested in how the values of these ambiguous options are encoded in the brains of individuals with PTSD. And she could do this because she could take the choice data and fit it with a behavioral model. The model itself is not really important. What's important is that we model the subjective value of different options as a combination of objective parameters of each trial and subject-specific parameters that account for the risk and ambiguity attitudes, and we use that in a choice function. So you can get the subjective values out of this model, and then you can look for correlation in the brain between activation and subjective value. And Ronan looked specifically in value-related areas that we all are familiar with, and she found something interesting in the ventral striatum. In this area, the strength of the correlation between the bold signal and subjective value reduced as a function of PTSD symptoms. And it's not just that it was reduced, it actually changed sign. So it went from positive correlation to negative correlation, which to us suggesting something potentially interesting, perhaps a shift from value representation to saliency representation in PTSD. And what do I mean by this? So if you want to represent value, this is the blue line here. I don't know if it's, you want higher activation for higher rewards and lower activation for higher punishments. But if you want to represent saliency, you want higher activation for both higher rewards and higher punishments. And interestingly, prior research has shown both representations in ventral striatum, both value and saliency are represented there. So Ronan went to the brains of our subjects, and now she divided them based on diagnosis, PTSD versus controls. And she looked specifically at value and saliency encoding and found that indeed there was enhanced representation of saliency in the brains of individuals with PTSD, here in blue, and enhanced representation of value in the controls in here in red. Now, this should be taken with a grain of salt. It's exploratory, it's initial, but it was interesting to us because it's reminiscent of similar findings from rodent research following stress manipulations. So why am I showing all of this? Just to say that using this kind of paradigms can be very helpful in unraveling individual attitudes. For example, for PTSD, we used an economic decision-making that had nothing to do with the trauma, and it told us something about PTSD symptoms. However, of course, these paradigms are limited in many ways, and I'll talk about two limitations today. So first of all, most of the decisions that we make are not about money. More than that, they're not even about quantitative outcomes. So even prior studies that did look at non-monetary outcomes like food and medicine used quantitative outcomes like the number of M&Ms or the number of milligrams of medication. And we're interested in the kind of decisions where potential outcomes are not quantifiable. We have several projects in the lab now looking at decisions about medical treatment. I'll talk a little bit about this. The other limitation is that, with all due respect to risk and ambiguity, they don't cover all the types of uncertainty that we experience in real life. For example, sometimes we don't even know what the potential outcomes are. And this is something that Ohadan, a postdoc in the lab, who's also here, presented a poster about on the first day. If you haven't seen it, I encourage you to talk to Ohad. He designed this novel paradigm that looks at these kind of decisions. Another type of decisions is when we have conflicting information. Another type of uncertainty is when we have conflicting information from different sources. What do we do then? So I'll talk a little bit about this. Okay, so in the remaining time, I'll talk about these two ongoing lines of research in the lab: decision-making with qualitative outcomes and decision-making under conflict. So for qualitative outcome, we came up with this hypothetical scenario. We tell subjects to imagine that they were involved in a car accident, suffered from a severe spinal injury, lost the motor function of their legs, and so they're rushed to the hospital and they have to make decisions between potential treatments, because if not, they'll remain paralyzed forever. So this is how the trials look. On each trial, subjects need to choose between a short treatment that is bound to work but can only provide slight improvement, and a probabilistic treatment that can provide a better improvement but may also not work at all. And to make it comparable to the monetary decisions, we have both a risky condition with known probabilities and an ambiguous condition with unknown probabilities. The main difference from the monetary paradigm is that the outcomes are verbally described, and these are the potential outcomes. So for example, major improvement is defined as after the treatment you can stand and walk without assistance for the distance of several blocks, and so on and so on. And this was defined with a physician at Yale, Terry Fried, who's helping us on this. And so subjects read these several times and they're asked questions and they have to rank the outcomes, and we have good evidence that they understand what they're doing. And this is the first study using this by Ronan in the lab in a small sample, just to show that the paradigm works. So what I plot here is a proportion of trials in which subject chose the risky option as a function of probability in both the monetary and the medical domain. And subjects were very lawful. They chose options with higher probability more. Interestingly, they also showed ambiguity aversion in the medical domain, very similar to what we see and others see in the monetary domain. So what I plot here is the difference between choices made under ambiguity and choices made when there is no ambiguity and outcome probability is 50%. And why is that? Because if you're not affected by ambiguity at all, there's no reason to assume that the line here between the red and the blue is anywhere but in the middle. So someone who's not affected by ambiguity will behave as if, I pressed something wrong, behave as if, the outcome probability is 50%. So if we see negative numbers here, it means that subjects choose the ambiguous options less. So they're averse to ambiguity. And if we look at the correlation across domains, risk attitudes in the monetary and medical domains, ambiguity attitudes in the monetary and medical domains, they're significantly correlated. It's not a huge correlation, so it's consistent with the idea that there is some general risk and ambiguity attitudes across domains, but also maybe some modulation that are domain specific. And Nachshon Korem, a postdoc in the lab who presented a poster yesterday, extended this to a lifespan sample, basically showing the same correlation across domains with no age effect in this. Chelsea Hsu, a graduate student in the lab who is about to graduate in 2 weeks, was interested in how stable these attitudes are across time. And so during COVID, she collected data on this online and basically replicated, this is the first phase where subjects did this online and basically replicated the correlation between risk attitudes in the monetary and medical domains and the same for ambiguity attitudes. And she had around 400 subjects who then came back to do the experiment 9 to 10 months later. 300 of those came back and the results are very similar in phase 2. And then when you look at the correlations between phase 1 and phase 2, there are significant correlations. These attitudes are at least partially stable across time. Interestingly, perhaps more stable for risk than for ambiguity, may be consistent with the idea that risk attitudes are kind of a personality trait. So just one more thing about this, a challenge in studying this kind of decisions is how do you model them? And why would you want to model? If you want to do something like what I showed in the PTSD study, where you want to put a number on each subject and then correlate this with, for example, symptoms or other things, tendency to curiosity and so on. Or if you want to look at values in the brain or at latent variables in the brain. And so you need some kind of way to model behavior. And we can use models like this, like we did with the monetary decisions. But the problem is that we don't have a quantitative amount to plug in our model. So how do we deal with these qualitative outcomes? There are different ways to do it, different approaches. What we found to be quite successful is to simply fit the outcomes as additional parameters in the experiment. And we have several projects ongoing now doing this. This is just to show you some preliminary work. For example, if you get the subjective value out of this model, you get the expected curvature in the monetary domain suggesting that that could be useful for the medical domain as well. You get ambiguity aversion out of the model, and ambiguity aversion is correlated across domains, just like we saw in the model-free analysis. And interestingly, if you explicitly ask subjects to estimate the probabilities in the ambiguous trials, these estimates correlate with the ambiguity attitudes that we get out of the model. So just some checks to see that these models can work. What Nachshon presented yesterday, if you've seen the poster, is that including probability weighting in the model, and I apologize for the typo there, might actually improve these models even more, but this is ongoing work. Okay, so this was about qualitative decision-making, and the few remaining minutes, I'll talk about decision-making under conflict. What do we do? This is led by Ohad, together with Maya Sangvi, a former undergraduate student in the lab. What do you do when you have conflicting information? One person tells you the past probability for getting $21 is 10%, and another person tells you, no, it's actually 90%. So one option is that people turn this into an ambiguous situation and assume that the actual probability is somewhere between these two extremes. It's also possible that these are different mechanisms, independent mechanisms where people do something different. And so Ohad and Maya designed this paradigm where on each trial, subjects choose between a certain option, 100% chance of getting $5, and an option on which there is conflicting information. One person says one thing, another person says another thing. We also had an ambiguity condition where the choice is between the certain option and an ambiguous option, so we can compare conflict and ambiguity. And we had a risk option with 50% chance, so we can correct for risk attitudes in our analysis. And for both conflict and ambiguity, we had 3 levels: strong conflict or high ambiguity, going all the way to low conflict or small ambiguity. And these are some initial results. This is in a group of more than 200 subjects collected online. What we plot here, x-axis is the proportion of trials in which subject chose the conflict option over the certain option, and this is the same for ambiguity choices. And importantly, both proportions are corrected by risk attitudes. So what I plot here is the additional effect of conflict and ambiguity on choices, and you can see that this is strongly correlated across subjects, suggesting that there is, at least to some extent, some common mechanism for these choices. Interestingly, you can see that more than half the points are under the diagonal, suggesting that in this case, subjects choose the conflicting options a little bit more than they tend to choose the ambiguous option. However, we also had trials in which subjects had to directly choose between conflicting option and an ambiguous option, and there they were very averse of conflict. They chose the ambiguous options much more than the conflicting options, suggesting perhaps maybe a reversal of preferences, or maybe conflict aversion is especially elicited when it's conflicted, when conflict is compared with some other option that doesn't involve conflict. Okay, so there is correlations between attitudes toward conflict and ambiguity, but conflict aversion is stronger when directly contrasted with ambiguity. Okay, so to summarize everything, I wanted to show that there is significance for studying risk and ambiguity in psychopathology as an example for how this might tell us fundamental things about individual differences. And because there are consistent attitudes across domains and across time, these studies might tell us something that is real, that is meaningful about the individual, that is not specific to a specific domain. I've also shown you similarities and differences between ambiguity and conflict, and I think it's interesting to think about how these similarities and differences may affect the tendency to seek information, to be curious, or to inhibit this tendency. And an open question in all of this that you may be asking is to what extent these attitudes that we study in the lab, in the absence of any learning, in the absence of any opportunity to explore, to seek information, in what extent these attitudes actually tell us something about what people do in the context where they are able to learn. And this is something that our lab is very interested in, and so we have several ongoing projects where we look at decision-making and learning together and try to associate individual differences in the two. And finally, I just want to thank everybody who did the work, especially my amazing lab, current and former members, and some great collaborators. And thank you.
Okay, so three quick questions. Let me pose them all together. As an economist, I would have zero doubt on how to model because of unknown value. I would assume that the agent has a value. We don't know it. We're trying to elicit it.
Yes. Mm-hmm.
But then as an economist working on ambiguity, I would probably guess that the value is ambiguous itself.
Okay.
And therefore, I would build up a model that compounds the two and allows for interaction. And so I'm interested to know if you thought about it, and there's a lot of wealth of information here that would be very cool on this interaction.
That's fantastic. We've thought of it in very general terms. We haven't done any modeling like that. What we did in addition to what I presented is, for example, ask subjects to rate their outcomes and then use that in the model, or even just using some arbitrary values and put them in the model. Everything kind of works. This seemed to work the best, but you're absolutely right. Including ambiguity about the outcome would be fantastic. And if you're willing to talk more, I would love to.
Yeah.
Great. Thank you.
Hi, I'm Jacob Elsey from Johns Hopkins. I really enjoyed your talk, and I thought the part about salience was really interesting, and it kind of reminded me of like the concavity of the curvature, like in prospect theory, as opposed to the gain or loss domain. And I'm wondering if you've looked at, if there's any maybe attentional-driven features like of the salience in like gain versus loss domain, and if there's a way to dissociate that from just kind of general risk preference.
That's a really great question. We haven't looked at anything like that, anything about you mean about the stimulus itself, just like sensory perceptual saliency. We're very interested in this. We didn't look at this. I don't think specifically in this that there should be such differences because the stimuli are very, very similar to each other. We did think of this more in the context of, for example, different ambiguity levels. If there is something about the stimulus that is different, also even different risk levels. So you have two numbers, two parts of the stimulus that are important where the outcome probability is 25 or 75%. You have only one part that is important when it's 50%, for example. So this might affect saliency in the perceptual sense as well. So I think this is a great idea, but I think we'll probably need slightly different design to directly look at it.
Thank you.
Hi, thank you for the talk. Joy Gang from UC Davis. I was actually wondering if you could just say more about the ambiguity tolerance and attitudes, and whether they tend to be stable or they tend to be sort of context dependent, and if so, what are the key sort of ingredients that dictate individual differences in that context?
That's a great question. So we don't have a full answer to this, but there is some kind of anecdotal evidence suggesting that maybe they're less stable than risk attitudes, and we don't know to what extent. So one thing, I show the correlation between risk attitudes and structural features of the brain. To my knowledge, nobody has found similar correlations for ambiguity. We tried and couldn't find anything. Another thing is I briefly mentioned a paper from Paul Glimcher and Anna Konova. They repeated the risk and ambiguity task many times. Risk attitudes were very stable. Ambiguity attitudes, that was specifically in opiate users, did change transiently. And so suggesting also that this is more context dependent. My guess is maybe there is a combination of something that is more trait-like, stable, and maybe related to development of some of the psychopathology, and then something that is more transient. But I think we don't really know, and that's a really good question.
Thank you.
Great talk. I really appreciate that. I'm far removed from the field, so excuse my question. But I was just sort of wondering if in any of this literature or in your studies in particular, whether you characterize people's propensity to simulate the future, to simulate different outcomes, and how the reason why that occurred to me was in relation to PTSD. If people, to what degree does a pessimistic outcome on one future versus an optimistic versus not even considering the future kind of factor into all of these things?
That's also a great question. We haven't done that. Some people looked at that, especially in the context of temporal discounting, that maybe you discount the future more or less depending on your ability to simulate the future. And it's interesting, especially because the brain areas that in the value community we think of as value areas, especially VMPFC, are also and PCC are also the same areas that Dan Schachter has shown, for example, for both episodic memory and perspective thought or simulation of the future. So I think that's very relevant, but I don't think in the context of PTSD, at least I don't know of anybody actually looking at it directly. It's a great direction.
Hi, Floris de Lange, Donners Institute. Great talk. So you focused, or you showed very convincingly this ambiguity aversion, right? That people don't really like ambiguity. At the same time, so we also heard a lot of talks where people actually seek out more and are more curious in a situation of higher uncertainty, right?
Yes.
And I can kind of see how those two things can coexist, but at the same time, I'm curious, do you see them as opposing forces? Are they anti-correlated within individuals? What are your thoughts on that?
That's a great question. That's something that we think a lot about. Why do people like behavioral economists show ambiguity aversion, and then people who study reinforcement learning show this, bonus for exploration? And several people talked about this. And so, of course, the context is very different. In exploration, you can actually get information, you can learn, so exploration is really good. So you should like to explore and you should be open to uncertainty. And then in our task, there is no feedback, there is no learning. So, maybe there is no need to explore. But at the same time, I do feel like I would expect some association between the two. So, and this is what we're trying to study. is someone who's more averse to ambiguity in the context of decision-making like I showed, how would they behave in learning? Would that maybe push them to actually seek more information because they want to reduce uncertainty? Or maybe the opposite, maybe it will inhibit them from exploring because they don't like uncertainty and they don't want to deal with it. And that might probably be different for different individuals and maybe be different in relation to different psychopathology and so on. So I don't know, but I think that's a great question.
Yeah, there is also the other situation where there is actually no learning possible. So we've done studies where people cannot learn, but at the same time, they still are more curious when there's like a more entropic situation. So
yeah, you're right.
And it's probably part of it, but it doesn't explain the whole.
I agree. So, I mean, how do you think about this? To me, it's like contradictory to some extent.
I mean, one is about seeking information, the other is more about making decisions, right? So I could
yes,
even,
yeah.
So maybe that is but yeah, it's a fascinating question. Thanks. Yeah.
Thank you.
One last quick question.
From the perspective of cognitive load, I would expect ambiguity to be expensive, and that would predict why it's more transient. Because when you are relaxed, you accept more ambiguity. So an experiment that I would wonder if you might consider it useful is to create cognitive load and see whether ambiguity aversion goes up. It does not. It does. Okay.
Okay, so that was easy actually. So I'm not sure I'm familiar with it. So that's okay.
Okay.
Thank you.
Excellent. Let's thank our speaker again.
Okay. Hello. Hi, everyone. So firstly, I just want us to say that I've been having a lot of fun at this conference, probably the most fun I've had in a few years, and since even before the pandemic. So it's not just that. So I want to thank the organizers, especially Jackie, for putting this together. It's a nice, really, diverse and balanced set of speakers and talks. It's been really fun exploring new fields and hearing about things I don't normally hear about. So it's really exciting. Thank you. The second thing I want to say is that it's a little weird for me to come and give a talk. Actually, this one's mostly about experimental data that I don't have a complete theory for yet. Normally, I go to conferences, I look at experimental data, and I think, as a theorist, why does this happen? Why does that happen? I try to explain them. So here I come in the opposite role and hope that some of you can give me some feedback to tell me how to think about the data that we have. And I also want to say that it wouldn't be possible for me to present I think it's pretty cool, interesting experimental data without my experimental collaborators in Paris, Florent Manuel's group at Neurospin, and his postdoc, Alex Ponov, and master's student Maeva Lotelier. So how does this work? Oh, right. So I think I've told quite a few of you, a few times that I've moved to Darmstadt. And maybe some of you remember this by now. So when I told everybody about this, or one by one, people were very surprised because I moved with my family, my 2 kids, my husband. None of us spoke German. Well, I spoke a little bit from college, but you know how college language classes how much it actually teaches you. So it was dealing with a new language, a new jobs actually for my husband too, trying to have a new friend network, get a new house, deal with this kids' schools, deal with the bureaucracy, the laws, the political system, and the school. You can see how I was so preoccupied when I made these slides about my children's schooling that I put it down twice without realizing. So when people heard about this, some people said, oh, how stressful. And other people said, oh, how exciting. And some said, oh my God, why? Why would you do this to yourself? And my longest and oldest and dearest friend said to me, yep, that's Angela. Who else would it be? So, I was a little disappointed actually, because I felt like I was making a really courageous move. And they were like, if anyone's gonna have an adventure like that, it would be you. So yeah, I'm not surprised. So why am I talking about this? It's because novelty or uncertainty can be appetitive or aversive to different people, just like we've been talking about all morning. And there are persistent individual differences. So I've been like this all my life, apparently, I didn't even know. So my high school best friend told me, yeah, of course, it's time for you. You've been at UCSD 14 years. I was surprised you stayed that long. So this talk, I'm going to be telling you about a particular type of decision-making under uncertainty, where you're making repeated decisions and they're stochastic noisy outcomes. And this applies to all kinds of decisions, like when you go to a restaurant or deciding what research project to pursue, or you're dating or something. And each choice not only gives you immediate return, but also gives you information gain. So you always have this trade-off between exploration and exploitation. And the way this is canonically studied in neuroscience psychology is using multi-arm Bandit task. So Bruno Averbach gave a nice introduction to this 2 days ago, so I'm very grateful, so I don't have to spend that much time on this. But as he mentioned, you choose one among a certain number of options that only the chosen outcome is seen, either reward, no reward, if it's a binary bandit. And you exploit, meaning that when you choose the option with a high expected reward rate, or you can explore by exploring unknown options, and that gives you information gain. And I think I see also, did he mention this? So when you have a stationary bandit, and then you can, with a stable reward rate, then the optimal decision policy is actually known. It's Gittins index. You should basically take the expected reward under Bayesian inference of each arm and then add to a particular amount of uncertainty bonus. So a coefficient times the standard deviation of your posterior uncertainty. So, but in the general case, when it's non-stationary, then there's no known solution. And in fact, the non-stationary case is a much more interesting and realistic case, because things are changing all the time. Like how exciting a reward project is going to be is probably not going to be the same all the time. Same with the quality of the restaurant, the ownership might change. And who knows, your partner may not be the right partner for you anymore because you've changed or they've changed, who knows, right? So it would be terrible if, well, hopefully not, hopefully you can grow together. But anyway, that's a different conversation. So in the general case, there's no known solution, but you still have the sense there must be some value to exploring, and especially in a changing environment, it's probably even worthwhile to actually to explore unknown, less known options because things are changing. So what used to be good is now worse than the alternatives, right? So what do people actually do? As we just discussed, there's conflicting results in the literature. There is evidence that it depends, of course, on the task, whether it's learning or not, we just discussed, and what kind of uncertainty it is exactly. But even in the restricted case of a bandit task, where you have a finite horizon, there's also inconsistency in the literature. So for example, Bob and his colleagues he's here and chaired the session a couple of days ago. They had this very interesting paradigm where they vary the horizon of how many free choice you will have after 4 forced choices, right? And you can manipulate exactly how much information or uncertainty you have about each by specifying how many times you had to look at one option versus the other. And they found that the longer the horizon is, the more people seem to accord uncertainty bonus to the options. And it was indeed positive. But there's also ample evidence in the literature that there is no uncertainty bonus in the multi-arm bandit task regime. In particular, it seems to happen when there's non-stationarity in the environment or in the reward structure of the task, and there's a longer horizon. So this was one of the earliest studies that looked at this, where they found no evidence justify the introduction of uncertainty parameter. So we came up with a novel task. So here's our, it's a variation of a bandit task, more like the one that you saw on the previous page on the right. So there are 2 alternatives. There are 3 true reward levels, 30, 50, or 70 points. And it's a Gaussian distribution with that mean. And there are integer outcomes between 0 and 100. And there are change points about once every 24 trials. And they're interleaved forced and free trials. So, oops. Oh, it's, how do I actually? Well, I hear the beep instead of seeing a laser pointer. So, does anyone know where the laser pointer is? Bottom of my index finger. I'm not good with gadgets. That's why I'm a theorist. I'm really bad. Right. My husband does all of the IT support. Where? Okay, thank you. Okay. Yes, I discovered years ago, that's why I'm not an experimentalist. Things break when I touch them, I don't know how to make them work. Okay, anyway, so gray is forced trials. They're interleaved 4 trials, they're forced trials, and 8 trials that are free trials. And so there are 2 options. Their true reward rates is the straight lines, and then what subjects actually observe depends on which one they chose. And you can see we have a low noise condition and a high noise condition. And we tell them what the noise level is. And in addition to the typical, make your choice, we also ask them to occasionally report their estimate of which reward level each arm is, as well as their confidence about their estimate. And there are 12 blocks of such sequences of 96 trials. And they do it twice. They come in once in a behavioral session where we also give them some questionnaires, and they come back a second time where it's a little slower paced for FMI, and they do 4 more blocks. So there are 54 such subjects, and we collected not only the behavioral data, but also a bunch of questionnaire answers, as well as pupilometry. And there's also FMI data, but that's more preliminary. I'm not going to be talking about it in this talk. By the way, this whole talk is a preliminary. It's the first time I'm giving this talk on this data at all, so bear with me. I can't make heads or tails of this data either, so let's go together. Okay, so what's important here for modeling is that we used a Bayesian ideal observer model, but unlike in the stationary reward case that Bruno described 2 days ago, in this case, we don't have sufficient statistics. So you have to discretize the belief space and use Bayesian update, or sort of approximately to update your beliefs. And the sample mean and the number of trials you've seen so far are no longer sufficient statistics. So it's a little more complicated, but it's not that complicated. Anyway, so we use a Bayesian iterative updating algorithm. And this is, for example, illustrating what the posterior distribution of the 3 reward levels are in the ideal observer model for option A, which is red. And this is what the distribution looks like for option B, which is purple. So they were always given purple or red options that as luminance, so we can do pupilometry properly. So in this case, we would say the subject has more estimation or expected uncertainty for arm A than for B, because as you can see, there's more entropy. We tried different measures of uncertainty, either entropy or 1 minus the map estimate probability, and it didn't really change any of the analyses. So for simplicity, we just assume it's always the 1 minus the maximum probability. Okay, so first we want to see, well, is our model any good in predicting what subjects believing and choosing? And what we see is that, this laser pointer is not very bright. Okay, so if you look at the ideal observer, you see, and you chose the map estimate as your choice, then it will correspond to which arm has truly, what the true reward rate of the arm is, slightly lower than 2/3 of the time. And we're using this as a reference performance because subjects don't know what the actual generative reward rates are, so that correspondence is lower, but still better than chance. Whereas if we compare subjects' self-report compared to what the model says is the expected reward of that arm, then we see the correspondence is about 61%. And if we asked about subjects' confidence, we can see that's also positively correlated with the ideal observer's model. Uncertainty, which is 1 minus expected uncertainty or estimation uncertainty. Any clarification questions so far? Okay. So what we're really interested in this task is actually to model decision making. So how do people make decisions under uncertainty? One possibility is that what drives their choice is expected reward or relative expected reward between the 2 options. And that, as different people have mentioned a few times, can consider that as exploitation. There's also relative estimation or expected uncertainty difference between the 2 options. And so it's a type of direct exploration. There's also total uncertainty, which is you just have no idea what's going on because both arms, you're pretty uncertain about their actual reward level. There's also reward prediction error. So obtained minus expected reward, that's the typical reward prediction error. Then there's sort of the surprise or unexpected uncertainty signal, which is despite the fact that you were uncertain about the expected reward rate, you're still surprised because of the outcome. So it's the absolute value of the reward prediction error. And there's also a repetition bias. We found that really helped with the model fit, which that people tend to persevere on top of all the other factors we put in. So so then we have this logistic model, which eventually ended up looking like this, right? So you had this constant term, this repetition bias term, this relative expected reward term, expected uncertainty term, total uncertainty, prediction error, and unsigned prediction error. And we started with the simplest possible model, which is their choice only driven by the tendency to be motivated by relative expected reward plus a repetition bias. And we include additional factors at a time. I used leave one out cross-validation on test data, on test runs actually. And we found that actually in the end, each factor helps to make incremental contribution, so we kept all of the factors. Okay, so now is the more fun part. Okay, what does the data actually show us when we did this model estimation? And so what we find is that, as I said, people have a strong tendency to repeat. This is the individual dots, the different subjects, and the bars are the averages. And they also have a tendency to be driven positively by expected reward, as you might expect. In terms of uncertainty, this is the estimation or internal expected uncertainty. We found a small but significant negative coefficient, so people are slightly uncertainty averse. But what was interesting is because we had 2 sessions, we can look at the estimated uncertainty or expected uncertainty coefficient. We found there was pretty high correlation. So, and what was interesting about this is that even though on average people looked at it, they were slightly aversive, if you look at them individually, they had highly self-consistent and fairly heterogeneous preference or aversion to this type of uncertainty. And in fact, this was true for almost all the coefficients we tried to estimate. They were all very self-consistent across the 2 trials. So for example, also in terms of the surprise, the unexpected uncertainty term, we also found that there was high, well, on average, they had a slight tendency to prefer that type of uncertainty, but overall there was a large heterogeneity and this low self-consistency. And for reward and prediction error, it was always a positive coefficient, and everybody was basically positive. It depended on, they just varied in terms of how positive they were in terms of their preferences for reward. Okay, so then we thought, well, can we explain any of the data using a slightly simpler win-stay lose shift strategy, which we have previously found that sometimes also explain at least the subject's behavior. And one hint that this might also be happening for some of the subjects, where on some of the trials, is that the reaction time was shorter on win-stay lose shift, because it's a simple heuristic. You don't have to compute or keep track of anything. So we think it might be a less effortful heuristic. We also, well, would maybe expect that at least win-stay should lead to better performance in general. But what we found surprisingly, is that lose-stay also led to better performance. So on the y-axis is their actual performance to total number of points they earned. On the x-axis is their tendency to either stay after they saw a better outcome or saw a worse outcome. And you can see that being more perseverant, or more persistent in this task always led to, on average, well, across subjects, better performance in the task. So win-stay lose shift is overall maybe a cheap, inexpensive heuristic, but not very helpful in this task. Then we also tried to look at, well, was some interaction between what the outcome was, how much it was better or how much it was worse on the left, that determined whether subjects tended to stay more or switch more. And what we found was if we subdivide the subjects by a median split of how probable they were going to stay or switch after they saw a better outcome than previously, then we found that there was actually an overall tendency to stay more for the Rust subjects who are the above median in all outcome scenarios. It did not depend on how much it was worse or how much it was better. And in fact, and unsurprisingly, the tendency to stay, whether it was better or worse, was highly correlated among subjects. So one way we try to think about why do some subjects repeat. When you stay, you're basically repeating the same choices over and over, right? Why might some subjects repeat more than others? One possibility is because they think the world is less volatile than subjects who switch more. And we find that that's indeed the case because there's a negative correlation with the volatility parameter we estimated in a Bayesian model for every subject. What's worth noting is that in this task, as well as all the other previous tasks we've done, where we use a similar Bayesian ideal observer model with assumed switch points, is that people almost always underestimate stability of the environment. And I have a whole other talk, maybe you have seen it before or not, or in my papers about when people do this, basically always, and why is that actually sort of helpful in general from a theoretical point of view. But so what it means is that these subjects who are more persistent are actually closer to having a correct estimation of the true stability of the environment. They're underestimating stability less than the subjects who think it's more volatile. So that's probably why they're doing better in the task. Well, so we actually had a whole bunch of psychiatric and personality questionnaires in this task. And you can say, well, you can get a bunch of significant correlations. Maybe it's just, you have so many comparisons. But actually what we find is that this tendency to repeat was positively correlated with agreeableness and not be correlated with all these different things that you don't want to have or to score very high on. Whether it's about, so W-FRIS is a scale for how negatively impactful ADHD type symptoms impact your life, either in your family life or in your self-image. Also, both state and trait anxiety. This is schizophrenic type behavior and neuroticism. So we thought that was interesting and may have something to say about transdiagnostic psychiatric traits. Okay, so then I want to tell you a little bit about the Pupilometry, which is even more puzzling. So here what I'm showing is the pupil response after the reward outcome for either better than expected outcome or worse than expected outcome, and then subdivided into whether subsequently on next trial they decide to stay or switch. And what you can see is that pupil response depends on both outcome and action intentions, whether you intend to stay or switch. There's no main effect of outcome or action. There's only a significant interaction. And in particular, if you decide to stay after it's better or switch after it's worse, those two, the red and the blue, are what elicit the largest pupil response. Okay. And then we further sort of separated out the trials according to forced trials and the free trials. And the difference was actually pretty striking because you can see actually, so this is actually just a pupil response after a visible switch trial. So switch happened during a forced trial period, right? So they observed that there has been a switch point. And it could either be a low to high switch point or high to low switch point. And what you can see for forced trials, the pupil response was much larger in blue for the low to high change point and the high to low change point. And it's just the opposite for free trials. We think that maybe this is because without action selection, because they don't have to worry about which action to choose, only try to keep track of the the reward rate of the different options, so you're only doing learning, then the pupil response is driven mainly by expected reward, right? Because low to high indicates a much higher overall increase in reward. And the AQ is an autism questionnaire. This I don't really understand at all, but the score on, so the more autistic you appear, the more it's positively correlated with this difference. And agreeableness negatively correlates with this. And the both traits are uncorrelated with total rewards earned. So for free trials, as I said, it's just the opposite. And our interpretation for this is that when you had to make a choice, notice that these two situations are asymmetric. If it's high to low, you don't have to take any kind of special action. You just repeat. People tend to repeat by default anyway. But if it's low to if it's high to low, then you do have to decide, oh, I'm going to switch now. So we think that perhaps this pupil response is induced by the plan to switch on the next trial. Okay, so one more puzzling, very puzzling experimental result slide, which is that the pupil response, there were individual differences that depend on how likely the subject was to repeat or stay. So the subjects who are more likely to stay after a better outcome have a larger pupil response prior to stay than switch choices. But the same subjects, because these two are actually highly correlated, they have larger pupil response prior to switch than stay choices when the prior observation is worse. I don't know. So that's one of the puzzles we have. I'm not sure exactly what it means, but it's very interesting. It's a very striking and strong correlation. Okay, so to summarize, there's been a controversy over existence of uncertainty bonus versus a penalty or aversion, especially in the long horizon non-stationary Bandit tasks. What we find is that indeed there's a diversity across subjects and the average effect is not very strong, but the people are self-consistent. And this may be why previously when you look at the population on average, you don't see a strong effect or the results are conflicting. And the pupil response seems to depend on both outcome and planned actions and interacts with the individual tendencies to stay and switch, as well as what they plan to do on the next trial. And there are also substantial differences in how individuals are motivated in exploring or adapting changing or noisy environments. So to summarize that part, the ability to stay the course, regardless of good or bad outcomes, in a noisy non-stationary environment seems to correlate with better performance in both our task and having fewer real-life problems, according to our psychiatric questionnaires. So these are my PhD students and a former postdoc who worked a lot on this project over the years, and my collaborators in Paris, and we were in this together from the beginning, where we wrote a proposal and we designed experiments. We had many pilots, changed experimental design, waited out the pandemic to collect the data, and then now doing the data analysis and trying to make sense of it. And the funding was originally from CRCNS. For my part, was from NIH NIDA, and for Florent's group was from the French National Funding Agency, I forget the acronym, and some funding from UCSD, as well as the ALPHA, the Alexander von Humboldt Foundation, which funds my chair since last December. And I have openings because I have a new lab. Please email me if you are interested or know anybody who might be interested. I'm ready to take questions. Thank you.
About 5 minutes for questions.
Yeah, sure. Hi, there was a set of very interesting and also, as you said, puzzling data, but we're scientists, so we love puzzles. The thing I'm really interested in, the findings you had about how there was this variation in the fitted weights in that model between individuals, but it was stable across sessions, so the people were using a consistent strategy. And I'm wondering, if you look at the correlation structure of those weights, do you see, so like one possibility is, a person has this weight lower and this weight higher, and the net effect is sort of partially cancel each other out in the strategy, so they end up with some partly similar behavioral patterns. But another way is that the person with this lower and this higher, those are both pushing them in the same sort of direction to extremes. So for example, some people being very good and some people being very bad. So I'm wondering which way it tends to go, if there's some tendency like that.
I mean, there are many scenarios in which, the parameter estimates could be correlated, either due to true correlation because of, just individual differences, or due to just, estimation, confusability or something like that. So we did do we did look at the correlation between estimated parameters, and it's interestingly, there's a positive correlation between expected reward, how much that matters for your decision, with both expected uncertainty and unsigned prediction error. So the people who are more driven by unsigned, reward are also the ones more driven by uncertainty, right? So that's I don't think that can be explained by either sort of trading off in real life, in the brain or in the model identifiability type of problems. So that was a little unexpected, but it's also kind of cool. And I think this may relate to the fact that it correlated with performance in the task, correlated with agreeableness, right? What makes me worry slightly is the subjects who were more keen on doing the task well and pleasing the experimenters, the one who really understood the task and really tried to make an effort, right? Because they're just getting points. They're not like, even if there's small differences in compensation, not really enough to really motivate people to really care about the experiment and do really well. If they don't care about being a good subject, basically. So maybe it's just the personality trait of like, I want to be a good subject and help these people with science, who's making them be driven more by all of these factors. I don't know. That's my.
Only you know how to recruit more of those people.
Yeah, I know. Introduce your friends to us, please.
Great talk. Great, rich data set. Lots of thoughts, but one thing that sort of stands out for me is the force trials during the exploration. We tried something not exactly like this, but a similar flavor of like random force trials in a kind of continuous paradigm a long time ago. And what we found sort of anecdotally is people just outsource their exploration to the force trials. So it's sort of like, I don't think about, I just exploit, and then when it forces me to do something else, that's my exploration. And I wonder, like in this paradigm, I mean, I guess it's, I don't know if they're random when the force choices come on. Maybe you could look at run length and things like that, but maybe that's something that changes the behavior in some way.
Yeah, so we actually designed the experiment such that half of the change points were visible, meaning that they came during the force trials. Yeah. And what that meant was that there wasn't very many stable force trial periods. So they're not very good actually for exploration in that sense. But if subjects realize this, I guess they would be able to take advantage of that. Yeah, I don't know. I have to go think about that. Thank you for the suggestion.
Hi, thanks for your talk. So I guess it's a bit of a question and maybe a bit of a suggestion, or I'm not sure if I've understood everything correctly here. But in terms of pupils, sometimes you'll see like increases in pupil size that are related to detection of an error. Like I made a mistake on the previous trial, for example. So I was wondering if it's possible that some of your pupil effects are related to how an individual perceives what they did as before as being correct or incorrect, given these other sort of traits and the trial types.
I would guess that that should come out. I mean, it might be washed out by other effects too, but I would think that would come out as a main effect of the outcome having been worse than expected, right? Because they're not real mistakes in our experiment, right? Because there's no correct or wrong answer. But if it's worse than you expect, it's kind of like a mistake. Like it's like, oh, I shouldn't have done that. Now I've chosen again, or I've chosen this new one. It's worse than what I expected. So we didn't see a main effect of worse versus better.
Thanks.
All right, well, thank you. Let's thank all three speakers again. 25-minute break, which means we come back at 11 for the final two talks, which will be followed by a discussion. General discussion.
The last session of the workshop before the panel discussion. And so the last two presentation will be back to a computational perspective mixed with human experimentation. And the first talk will be by Todd Gerekes.
Okay, great. Thanks so much. It's been a great workshop, and really excited that it finally came together. I'm going to talk about something that this is the first time I've given a talk about this topic before, so I'm kind of treating it like a stand-up, workshopping an idea. So that there might be some bad moments, but hopefully you can bear with me and give me feedback on it. So the work is about studying the structure of playful goals, and I have to give a lot of credit here to Guy Davidson, who is here in the conference, and he had a poster yesterday. He's been the lead on this work, but we're also doing it in collaboration with Brendan Lake and Graham Todd and Julian Toglias. So it's hard to give a talk about human learning without showing a photo of, whoops, actually I wanted to show that thing. Okay, let's see. How do I scroll my notes? I can. Oh, okay, you can do it. Okay. Let's see if you can make it visible. Okay, so can you make it smaller? No. I'm talking to somebody that you can't see. This is part of the stand-up. Okay, well, so it's hard to give a talk about human learning without showing a photo of some kids playing with blocks. So here you go. There's a kid, they're stacking blocks. They're probably learning physics and a theory of causality through self-directed play. You know the whole drill. But what happens when the camera crew moves on? So when mom and dad are tired of cheering, about the tower building abilities, and they go pour themselves a drink? Well, the answer is often more of the same, but in different combinations. And I'm supposed to see the other combinations. Let's see. Up, down, left. I think now it's on the other thing. There we go. Yeah. They might move on from the block stacking task to the block maze building task to the balancing blocks precariously on the edge of the table task to the building a tower train task or whatever. And it's long been recognized, obviously, often to the surprise of parents, that this type of innocent, kind of mundane play is actually incredibly important for learning about the world. So work by developmental psychologist Laura Schultz has long highlighted how it's through this kind of play that children actually acquire understandings of how objects behave, how concepts combine, and how plans can be made. From the vantage point of today's talk, though, I just want to highlight 2 points. The first is that this behavior, although seemingly aimless and undirected, is actually highly structured. So the kids' play almost feels like a little series of tasks or projects that they're conducting with a singular goal in mind, but with no really obvious connection to reward or even information. I think we've all come to appreciate the ways in which uncertainty and information drive information-seeking behavior in this workshop, but these types of playful goals, while supporting learning, have only a loose relationship to information gain, or perhaps even the learning progress. So the second point is that these tasks or projects, as it were, for these kids tend to build on each other. So once you learn how to build a tower, then you build new types of towers, and once you build a maze, you can design and navigate other mazes, and towers combine with trains to make endless arrays of problems for children to solve. So for the purposes of being provocative, let's imagine 2 extremes. So one's kind of like a generalized information-seeking drive or motivation. These things are going to be like many of the things you've heard about, like novelty bonuses, cumulative prediction error, learning progress, surprise, suspense, information gain. And we often think of such mechanisms as enabling a type of self-teaching or a curriculum by where a learner can keep pushing at the boundaries of their knowledge. And the other idea is like a mind that's almost in constant argument or dialogue with itself, such that some element is proposing ideas and problems, and another element is solving those problems and learning as it does so. So this latter proposal has a bit of a different flavor because the goals are meaningful to the learner and are highly structured. They have intent and purpose and like a rough assessment of a success, and such goals could easily be communicated to other people. So if you interrupt a child, playing, they might get frustrated and say they were trying to build a train tower and make it go in the maze, and less like there were 2 bits of information I expected when I put this block on this one. So of course, thinking of exploration in this way brings us to the thorny and terrible and no good problem of understanding what goals actually are. And in psychology and neuroscience, goals are a fundamental concept. We use them in our common language all the time when talking in psychology. And perhaps the most agreed upon definition is that goals are some kind of desired states that seem to fit. And that description kind of just seems to fit, but doesn't do a ton of work for us. In a review article in the even late 90s, authors discussed this kind of notion of goal in psychology as a notoriously ill-defined concept within psychology, and little progress had been made despite decades of work on that work. And partly this is because it can refer to like a whole bunch of different things like aspirations, personal goals, like one day owning a home. But for the purpose of this talk, I'm going to focus on kind of cognitive problem-solving type goal representations. And so the thesis that I'm going to try to advance is that we think a key to understanding exploratory play behavior is having a more faithful and complete representations of goals and sub-goals. So specifically, we think that cognitive goals are fundamentally abstract mental representations which enable environment-independent scoring of behavioral trajectories. They enable compositional generative capacities. They facilitate communication and can represent temporally extended behavioral patterns, and which will bring us to the punchline, which we think are well captured as computer programs written in something like a language of the thought. So let me just step through these things in turn. So to make this kind of clear, I'd like to just compare the notion of goal that we're advocating for against the more common one that you might have encountered within reinforcement learning literature. So generally in reinforcement learning, the goal is to simply maximize the long-run discounted reward earned in an environment. So people talk about rewards as specifying the task goals, essentially. So for instance, if we build a little grid world agent, we might say that we want the agent to arrive at a particular terminal location, the little blue location there. And to do this, we would assign a larger reward for entering that state. And while reward is often a good target for training systems, the word goal to refer to these setups is a little like obtuse, I guess, because it's not the only place where and this is not the only place where we kind of combine rewards and goals into the same language. So for instance, in inverse reinforcement learning, people build models of social goal inference where you watch the behavior of another agent, and what you're essentially trying to do is infer the reward function that's guiding their behavior. And we sometimes call that as like inferring their goal, but in fact, we're referring their reward function that they're using. So the blurring of goals and rewards is commonplace and even well accepted in literature. But the first problem with this is that equating the notion of a goal and reward function inherently links the goal concept to the environment in a highly specific way. So, you know, the goal is such that like the state 25 is worth 10 points or something like that. But human goal representations seem to exist at a higher level of abstraction, right? So we find it cognitively easy to talk about a goal like making soup, which can be met by different people in different kitchens with different utensils, using different cooking mechanisms and even recipes. And this suggests that what we want from goal representations is something that's more abstract and in particular what we would describe as environment independent. Second, it's known that people have a difficult time reasoning about rewards actually to induce goal-oriented behaviors in other agents. So for example, Andrea Thomas did these interesting studies over a decade ago looking at how humans provide rewards to RL agents performing some simulated household tasks. And people misuse reward signals like frequently in ways that like actually are maladaptive for actually teaching these like robotic agent reward maximizing agents to do things. So like the robot would like go into the kitchen and drop a dish, and then immediately the person would play lots of negative feedback saying, don't drop the dishes. But of course, because reinforcement learning in the Bellman equation sort of backs the value up from those states that are near the kitchen now are negative, and the whole robot just avoids going into the kitchen altogether, right? And so it's like the language of state-specific rewards is something that we kind of find awkward and clumsy and maybe even psychologically unfamiliar. So one feature that we want to preserve, though, is the nature of goal representations being an active representation that minimally can score behavioral trajectories. So reward functions have this property in standard reinforcement learning because you can take a sequence of actions that an agent takes through the environment, and you can record which states they transition to, and looking it up in the reward function, you can find out how much those transition states were worth, and you can come up with a total sum or score sort of for that behavioral trajectory under the reward function. However, you think about goals in a more abstract way, what we really want is a scoring function that can apply to many disparate situations while still providing the scoring functionality. So that's why we call this environment-independent scoring functions. Like what we want is to be able to do the same thing in an environment-independent way. So we want to recognize all these different situations with different numbers of states and so forth as all going to the target location, right? Yet another point is the creative generative capacity of human goals. So think of a goal for yourself or someone else. I like to think of like giving a good talk while playing this piano, for instance, or raising a child while having a successful career. So, you know, goals come to mind for us easily, and they flexibly combine elements that we've experienced before. So these combinations aren't entirely arbitrary. So when we think of a goal that someone else might have or a goal that we might want to have, it's actually hard to think of goals that are really nonsensical, like growing an avocado plant in your shoe or something like that. Like in principle, yes, but in practice, we seem to think of goals that combine in sensible ways that seem to guide children's play to some degree as well. So when you look at the kids playing, they're not doing like crazy things with their toys. I mean, they sort of like from an adult perspective, maybe it seems a little bit weird, but they're like stacking, blocking, banging. There's this range of behaviors that are sort of building on each other and building in sophistication as they continue to engage with that ability. And on this point, we've really been inspired by the work of Pierre Yves and Cedric Collas, who are here about using language as a tool for structuring creative problem proposals. And they argue that, you imagine that what you really want is a system that can propose for itself out of distribution goals. And the key way of doing that might be to leverage the compositional features of language in order to enable that to happen. Along the same lines, we can communicate about goals. So this might be salient for older children, but the interplay between language and goals and rewards is still a relatively underexplored issue in psychology. So for example, when someone performs a task, even a simple one involved in maximizing reward or information gain, they can often verbalize what they're doing to other people, however roughly. And the ability to communicate about goals, to describe what goal you have, or to learn about a goal that someone else has, seems to be critical to the representation of goals. And then finally, human goals are often temporally extended. So for example, consider a game a child might come up with, which is to like throw a ball and hit the wall and then land it into a bin or a bucket. So how to represent that goal in a standard reinforcement learning MDP framework is somewhat complex. So one idea is that we can make a state representation for each of the combination compounds of those different states, right? So you would have a state that's like hit the wall and goes in the bucket, that's worth +10. But you would also need to have combinations for all kinds of other things if you wanted to specify lots of different goals. You'd have to have like hit a wall and hits the wall and goes on the floor, hits the bucket and then hits the wall, which would just be an inversion of the desired goal states, right? So it gets unwieldy relatively quickly. And so what you really want is something that can like maintain temporal logic, basically. So like the fact that a goal can extend not just to be a single state that you desire, but a sequence of states. So like you want to do a 360 and then dunk the basketball, right? It's like you got to do it. You can't do it in the other order, and you need to do them in that particular sequence or whatever. So there's been ideas that have been exploring this in computer science. Planning with preferences is one way of thinking about it. It's kind of the same idea like where your Google thing would be like, you need to get to this destination, but you want to avoid tolls or something like that. Sort of like you have like other constraints that operate over the goal representation. And then Michael Littman and others have looked at like environment independent task specifications using something called linear temporal logic, which has been an inspiration for us. So anyway, so this brings us to the punchline, which is that like we think of the things that have these properties are going to be something like programs, which we think meet many of these design criteria. So programs have been used recently in many areas of cognitive science for tackling representationally complex situations. Programs are structured representations that capture the semantics and syntactic constraints and mental representations. Grounding abstract programs allows goal representations to be environment independent. And programs can be converted to reward scoring functions, basically. So we can like take a program as we reference it in a kind of like a programming language. We can convert it into like kind of a finite state machine that sort of like captures the like whether a particular reward a goal has been attained. And this kind of way of like, this can be automated basically. So you can have like a goal representation for any arbitrary goal representation. You can build this finite state machine that is like independent of any particular environment that can be used as a scoring function. So I've tried to convince you a central thesis here, kind of philosophical arguments that reward enough is not alone and not a convenient way for specifying our own goals or for how we would communicate to other people, and give some philosophical reasons to maybe think that more highly structured representations of goals may be useful for psychology. Recently, we've been working on a larger project kind of elaborating this general idea, and I'll tell you about one specific line of work looking at playful goal generation in humans. Now, goal generation is a little awkward to study in adults because if you just tell people like generate a goal, it feels a little bit unnatural. So in the studies I'm going to tell you about, we had people use a slight change of word, which we asked them to create games. And I'm going to tell you about those experiments. People generate creative new ideas for games, but for the current purposes, I think it's okay if you translate back to this more general issues of goals, because that's sort of like what we're actually after. So in the experiment, we had people freely interact with this like 3D environment. I'm going to start the video here and let it play while we're watching. So there's built on AI to Thor, and so people were able to freely interact with this room. The main environment was composed of this room that looks like this, with everyday objects like desks and chairs, but also other various things like toys and baskets and blocks and ramps and so forth. There's different room variations that we tried in the experiment that allowed different types of objects available. And the instructions were, after learning about the interface, they would go into this and explore this room for a while, and they were asked to create a game. And the game can only involve using the objects that are in the room, and they had to have a scoring system that would be applicable to a single player, so it wasn't like a multiplayer game or whatever. The interface, after they played and they interacted with the game, they would like give given a thing where they had to create a game actually in just natural language. So they had several optional sections of this like game elicitation. They would have like things like a setup, like so kind of like how do you initially configure the game room to begin the game. Sometimes that might involve like putting a bucket in the middle of the room or whatever it is. They would explain the game that you actually would play. You would describe the scoring system. They would rate how hard they thought the game was and imagine what their score would be if they played the game themselves. From this, we created, contacted 192 participants on Prolific. We got a whole bunch of data about the games that people kind of just created in these environments. And we also tracked the state action traces of to replay the participants' experiences as they were actually playing their own game, which we're going to use for another part of the data, but I won't talk about here. And then we created a novel, like domain-specific language to model the structure of those games. But before we turn to that, let me just like quickly look at the types of games that people come up with. So people are like they vary in both creativity and complexity. So some people come up with like very simple throwing games, like throw the dodgeball into the bin to score points. Every time you score a dodgeball into the bin, you get 1 point, and you lose 1 point for every 5 throws. All the way down to like relatively complex games like this one. You have to use these white and blue blocks to create a path from the bed to another location and not using these other types of wooden blocks, and so you have to try to create a path by kind of like launching these things and then being able to hop between the locations or whatever. So what we do basically is like we get these examples from people here that are like their descriptions of their game, and then we kind of translate them into this like language. And the language itself is a custom domain-specific language that we developed for this purposes, but it's heavily inspired by a language called the Planning Domain Definition Language, or PDDL. And it's basically like preferences over how things would go. So you have a section called setup, a section called constraints, and a section called scoring. And these preferences express like sort of sequential dependencies on like actually executing the goal in particular ways. And so once we do this kind of, and Guy had to do a lot of hand translation here to kind of capture the semantic meaning of these things, like to go from like these representations to these ones. But once we have it in this kind of like code representation, then we can do like kind of put it through like the data grinder and get some insights into what people do. So there's several seemingly non-accidental properties of the games that people spontaneously create that we interpret as reflecting common sense constraints on game type. For instance, like in games that were kind of classified as throwing games, people often hold and launch balls specifically, and other objects are not involved in those kind of launching games, whereas other objects were used for stacking. And so there's kind of like an object-specific relationship between how the games are composed in these particular cases, even though, of course, you can throw a block or whatever, but people still respect the kind of intuitive physics and the common uses of objects. There's also like quite a bit of compositionality. So if we can come up with like structures that appear frequently within these repeated patterns, and we can count how often they occur. And there's like a small number of like 4 structures basically that cover almost like 50% of the occurrences. So like basically there's a huge amount of, even though the games are basically unique, there's like a huge combination of like very specific kind of motifs, like throwing, bouncing, that kind of stuff that like people mention quite a lot. But then on the creativity side, it's kind of like the Zipfian kind of distribution. There's like a lot of games that have like only this one-time occurrence of this particular type of like preference structure. And to show you an example of like how the language captures this kind of compositional relationship, here's a preference here that captures, it's described here as a function name. It's like throw ball to bin. And it's basically there exists a dodgeball and a bin. You hold on to the ball, and then the agent will, at some point later, let go of the ball, and the ball will be in motion. And then once it's not in motion, it should be in the bin. It's basically expressing that like constraint in the goal. But then you can build like other ones. So you can throw ball from bin from desk, and it just adds that the agent has to be holding the ball near the desk before they throw it. Throw the ball from rug to rug. So they hold it on a rug, they throw it, and it has to be in motion onto another rug. Bounce the ball from the edge of the rug, blocks from rug without breaking. But basically the point is that you take these different structures and you can kind of just like compositionally change internal ingredients of them to come with like quite different meanings of games across these different situations. So then what we try to do is, using an approach that we've used in the past for studying question asking, we try to come up with like an energy function that like is parameterized by a set of vectorized features for each game. So we take a game, this kind of tree-like structure, we count like frequency of different kinds of occurrences and turn those into features. And you're trying to basically learn energy by minimizing the energy of real games, and then we made like kind of like fake games that were like distortions of the games that people actually made. And so we're almost like building like a classifier that's learning how to like assign low energy to human games and to like distinguish that from games that were algorithmically generated. And so it's kind of trying to separate in the space of energy functions and assign low energy to really human-like games and high energy to things that were not. And so this is an example of the energy scores after the model is like estimated, showing that like the real games are all kind of clustered with relatively low energy scores. So we're sort of like able to move them all in the same direction. And that also we're able to like, in the complete set of completely fake games, there's a little bit of overlap, but basically we're getting reasonably good separation here. And then we do things like search for new human-like games using evolutionary search. So what we do is to model the process of like somebody generating a new game from scratch. Like what we can basically do is come up with like take these tree structures and swap parts of them out. And you kind of like do a genetic algorithm search where you're sort of like going through different individuals, doing crossover mutation, cutting trees, regrowing trees in order to optimize some energy function to try to come up with new games that have energy scores that make them seem human-like according to these feature scores. And from that, we can come up with like some very human-like games. I'm going to talk through one of them, but this is an example of a algorithmically generated game. So this program listing here was completely generated by a computer algorithm, and we back translated it into English to compare it. And it's basically a game where people are throwing balls into the top drawer. They're trying to count how many balls they throw into the drawer of the dresser, and they get a certain number of points for different kinds of objects that they can throw into that thing. And it's kind of similar, but not exactly identical to some of the games that actually appear in the data set. So since I'm a little bit over time, I just want to point out that like, we're building towards this idea of creative compositional problem solving in terms of these like program-like goal structures. Thinking of goals as structured programs solves several open questions, I think, in defining the objectives of human behavior. These flexible representations enable problem solving, planning, and inference, but also can be used to generate novel tasks and goals for a learning agent. And future work is going to be exploring like sort of how systems could propose their own goals, then that could facilitate their own exploration and learning by essentially generating a goal for themselves and then learning to execute that goal would be one way of kind of generating a very structured exploration strategy. So I will stop there.
Hello. This is really cool work. In your intro, when you were talking about like the various things you want your conception of goals to accomplish that aren't in like standard RL, a lot of it was reminding me of like different forms of abstraction, like state abstraction and temporal abstraction that people have talked about in an RL world. How are you thinking of these things as related or not?
I think well, so I'm like in a weird hat where like I think I'm a really bad computer scientist and I read the computer science stuff and I'm always really inspired by it. And I take that back into psychology and think like, well, have people talked about this idea this way? And maybe computer scientists view it the complete opposite where they're like, I take ideas from psychology and try to turn them formal. But I feel like that in a lot of that stuff, exactly like state abstraction and temporal logic, like Michael Lippmann's work or something has been very influential in our thinking about this. But I think that in the psychology literature, at least, the like representational advantages that those things have for modeling human cognition haven't been really realized yet, and so that's what we're trying to do in this particular case. So,
cool.
I totally agree. Yeah.
Yeah. Hi.
Hi.
So yeah, this is great. So okay, so you began by saying how rewards are not enough, and like totally convincing. But it seems that so how do people track their performance? Like, I mean, are you approaching the goal or not? Right? It seems like you need some sort of thing like a reward.
Yeah. So I think like what's interesting is that the representation, like the like you need an abstract layer, I think, in order to like cognitively deal with these things more efficiently. And so like these games, like they're in these program listings, they do cross compile into what we call like a reward machine. So like the particular thing can turn into a finite state machine that can score a behavioral trajectory. So it can watch yourself or another agent play a game and can actually assign a reward. And so it can come up with a reward there, but it's like a downstream effect of that representation rather than starting at the low level atomic level of like saying like, oh yeah, there's a reward assigned to that particular action. There is a mapping between the two. So you do have like reward in the end. You're not like disavowing it, but the sort of like at the level of reasoning, proposing, combining, it makes sense to build a layer of abstraction above that which captures some of the more pragmatic constraints about
No.
how people deal with the world. Yeah.
Absolutely. It would be like really, I'd be really interested to see what this more abstract reward function looks like. So maybe in the next talk.
Yeah, okay.
Yes, and that's very cool, and sort of, I think, related to what Jackie was asking. I'm wondering, so if you have the agent and it's doing these sort of self-created games, it seems like there still has to be a motivational component deciding when do I give up, when is that game no longer fun, or when do I go to new one? When I was recently, playing games with my nephew, I was made very aware of that, so engrossed in one made-up game and then suddenly deciding, no, we'll do this other thing. So, and is there any about how that's decided, and maybe that sort of meta level of, what games are interesting and when they stop is where things would come in, like information gain or understanding.
Yeah, absolutely. Yeah. So like I definitely didn't, I did mean to make this dichotomy just for the purposes of being provocative, I think, but I think like you still need like motivational control mechanisms, but the question is like how to enable this like structured exploration and to kind of like realize that like the exploration behavior seems to be very like bounded relative to like what all the things that you could do, right? It's like sort of this I find this an amazing thing about human cognition is that like when you really think about it, there's so many more ways our behavior could express itself than we actually typically do. So we have the capacity to, but we just generally don't. And so those constraints are the things that you're trying to capture essentially. And so I think that the representational approach of this allows for a more structured form of exploration that will work better for modeling human cognition in a lot of ways. But yeah, exactly. There's still questions of like the degree to which curiosity and motivation still act as meta parameters that sort of control when you start and stop engaging these behaviors and so forth. But,
cool, thank you.
Yeah.
Thank you for your talk. I'm wondering if you think of your method as a antidote to the problem of latent learning, where agents or animals are not rewarded in their exploration. They find the result, find the goal, and they can rapidly navigate to the goal. So in that case, like, how do you think your structured goals can help with this problem of rapid learning, where you explore the environment and you can quickly solve it afterwards?
Yeah, totally. So I think that is in some degree like the potential for this, because you can do online learning. So like these children that are building blocks or whatever, they might be proposing tasks for themselves and then actually exploring. You can imagine a similar type of thing happening in kind of a mental simulation, right? Like where you sort of are like, proposing a goal for yourself. Like, I wish I could go to that other part of the maze, or I wonder what would happen if I turned on that door or whatever. And, there's a language, there's maybe even a congruence between thinking about that as like having some kind of, learning progress signal or novelty bonus or something like that. But there's just, again, it goes back to these representational advantages of using these kind of more structured things for like kind of making it seem like a real proposal, like almost like hypothesis testing or something like that in your mind, like saying, I'd like to go that direction, and then kind of thinking through and learning about the consequences of those imagined counterfactual situations or whatever.
Thank you.
Yeah, just to complement about that, something that's very important and efficient in this kind of goal exploration learning is hindsight learning, which is relating to counterfactual data, which is that even if you're trying to reach for a goal and you're not managing to reach it, in the meantime, you've done other things that you can relabel as maybe solving other problems or other games, and so you can learn all the time in a way.
Yeah, totally.
Thank you for the talk. Very interesting. And I really like the idea. I was just thinking so you were talking at the beginning about there's some constraints on goals, like they need to be abstract and maybe expressible in language and compositional. And I'm just thinking that programs themselves, they're Turing complete, so they don't need to be abstract. They also don't need to be in language. They don't need to be compositional. So how do you translate these? Like which constraints do you take, and how do you translate them into the language of programs? Are they built into the programming language themselves, or what are the kind of the constraints?
Yeah, no, it's a very important question, and probably one of the biggest empirical challenges for this type of approach is that getting evidence for so you pick a particular domain-specific language. We articulate it as almost like a hypothesis. So we think we do a little. I've taken an empirical strategy. What we've done in several of our projects that involve this kind of thing is take natural language and sort of look at the range of things that people expressed in a big experiment, right? And then sort of back out like what representational primitives do we need to get like basically complete coverage of the data set that we collected. And that's like kind of a like, you know, how many operators do we need? Now the question is like, there could be a slightly different coding of that, or maybe some operators are not available to people. So there is some work like in the kind of general probabilistic language of thought that people did where they were trying to like get evidence for particular constructions in the language, you know? And I mean, it leads you very quickly to like generative linguistics or something like that, right? Where you're sort of like trying to get evidence or attestation for particular types of representational strategies. And that's been an approach which, you know, you can debate whether you think that was useful or not, but it's like sort of, that's kind of what the whole game is about, is trying to understand the nature of a very complex mental representation. And I think that that's basically like the way you can do it. But I think as a proposal, you know, I think there's still a lot of work you can do to get like evidence for some of these representations, you know, with careful experiments, I think you can kind of reveal some of it. So yeah, I mean, that's not a perfect answer, but it's a difficult challenge, I agree. Yeah.
Thank you. So, sorry, Alan, maybe during the next break. So we need to close, so thanks again.
Yeah, thanks.
And last but not least, Daniel Poleni.
If you can hear me, I will prefer to stand here because I don't like laser pointers. I point to the screen, you can't see it. Ah, that I have to be here. Ah, right. Okay, then I'll have to. Okay. Okay, then I look like a televangelist. Good. Okay. So I will try to handle these objects here in the hand. That was not intentional. Anyway, I'm going to talk about empowerment and explain what it is, and the subtitle hopefully will become clear towards the end. Okay. Nope. All right. So that doesn't work. Good. Okay. How do we move forward? Yeah. Okay. So let me start thanking all the people that have contributed to this research. And especially to the last part, I would like to say special thanks to Stas Tjomkin, Ilya Nemenman, and to Tali Tishby, which had been were instrumental in the last part of the new research that I'm going to present today. And also this work was supported by various organizations, including several from the European Union, which of course is now a little bit more difficult to access thanks to Brexit. And for those of you who wondered what is how Hertfordshire is pronounced, it's pronounced like sneezing. Hertfordshire. That's the correct pronunciation. So let me start with the model that we are looking at. I have a relatively abstract model here. In basically, we have a very ambiguous. I will have a very ambiguous talk. Ambiguity is a topic, as we've seen. Part of it will be very intuitive, part of it will be very formal. So it will be basically hovering between these two extremes. And so to explain the formalism in principle, I will just first explain, if you look at the world without an agent, you can express it as a kind of Markov chain where you assume the W, the world, contains everything. So basically, the time progresses, and think of this as a Bayesian network. In fact, as a causal Bayesian network. So these are random variables, and the random variables causally affect the next one down the stream. And when we then introduce an agent, we can have the most simple form of an agent that is simply basically something that parameterizes the world dynamics. Here is an agent that essentially does the same thing in every step. There's no memory. So in other words, there's no time being tracked by the agent. And think of it just as an open loop agent that has a fixed policy, which can be chosen on a long time scale, for example, by evolution, right? Or learning, it doesn't matter. But what the agent does in the time scale of this picture is a fixed policy. Now, we can understand a little bit better what happens with the information balance of that system. And when I talk information balance, always think about this as a causal Bayesian network. So this node influences that node, and that node causally, and that node basically then influences the world back in conjunction with the previous step. And you can then look at the information balance of the system. And I don't have time to explain that in detail, but basically you can create equations or inequalities that tell you how the information, and here I'm talking about Shannon information. These are all random variables, so you can define that, how the Shannon information of intake of information through the sensor is influencing how much more you can do as opposed to when you have an open loop agent. Anyway, I'm just introducing it to make you familiar with the formalism that I need later. Of course, then there's a concept of sensors. Sensors actually limit what you can see about the world. They could be either engineered or it could be an evolutionary result. In many cases, you can just assume the sensor, this is often done, sees everything in principle from the world. But you can actually assume in some cases you don't. And then it's a POMDP. The question is it important? We'll see that it can have consequences, but I just mentioned it here for completeness. And finally, the most complete single agent model is when you introduce memory. So you see that there's a world, influences the memory. The memory is like the brain, and memory is unstructured. It could be anything. Could do anything with the past that happens before and decide anything based on the past and the current sensing input on what to do next. So this is the most complete discrete time Bayesian model of an agent, if you like. And essentially, the interesting part about that is a really high level of symmetry you see. Not only is it symmetric in principle, time reversal is something that's not obvious in these models, and it's of course hotly discussed in physics, but it's more important also to see that actually world and memory are virtually mirror images of each other. So the distinction between agent and world is a semantic one, it's not syntactic. That is a really striking aspect. Again, this is a separate talk, if you like, but I wanted just to point out that it's strikingly similar. So the world and the agent are really intertwined in a very tight form. And I want now to highlight two types of how you want to look at information and information flow in such a system. And so, for example, if you have a world that runs your memory, it's exactly the model that we had before, but you will see I have introduced rewards so that the people with reinforcement learning feel a little bit more at home. When you ask about rewards, you want to maximize, and now you can ask the question, how expensive is it for me cognitively to maximize it? So you can now ask, this is what I would call the relevant information. There are many variants of that. There's just basically everybody who looks at bounded rationality is actually confronted with that, with the question, how much can I get a value if I have limited information I can take in? How much information do I need to take in to solve a problem? Sometimes you don't need much information, sometimes you don't need any information. So for example, a funnel, basically when you put a funnel, you put the water in the funnel, the water finds a way into the bottle without much trouble. This intake information, this I also call pull information. Yes, pull information is basically how much information do I need to achieve a certain value. This is a very natural quantity to consider, and many people have done that in various forms. However, you can ask the dual question that is not quite as obvious what it means, but I will concentrate on that one in the rest of my talk. And that is the push information. So the push information is you have an agent and you're asking how much information can I squeeze to the environment and recapture. Now, why would anyone be interested in that? That is a question. It's not obvious to answer, but I hope at the end of the talk you will be convinced, yes, it's the right question to answer. I want to know how much information can I inject into the environment and recapture later on. So let me just start from a completely different perspective. And that was one perspective that motivated what I'm going to talk about today. It's not the only one, but this is probably the most plausible one. So in biology, the success criterion is survival. You survive, your gene line survives, that's what you want, nothing else. The concept of a task, we have been discussing about goals and tasks and so on. Nature doesn't have a task, it doesn't have goals, it doesn't have this. These are human concepts. So the question is, what do we, I mean, it's not sharp, right? The fact that you eat food, food is localized, that is a matter that, okay, happens because food stands at a particular location and you have to go there. But if you're a tapeworm and sit in the intestines, you don't need to go to the food. The concept of eating food is not a particular localized goal, right? You're just there and the food comes to you. It's basically like sitting in the airplane, right? You sit there and food comes to you. It's not a goal. You don't do anything for that. It just happens. The second problem that we find in biology is the search space is large and it is very, 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 very sparse. Rewards are not that common. We have some rewards we get immediately, but there are actually surprisingly few. And if you look at the beautiful examples we've seen in the conference, also in my predecessor talk, of goals being also generated by people, by kids on their own, it is really striking that where do you get the structure from your search space? And if you do a pure, let's call it naive Darwinism, because Darwin himself was not a naive Darwinist, by the way. If you do naive Darwinism, then Darwinism gives you feedback by death. Okay, you do stuff, and then you do something wrong, you die. That's it. Oof. It's a bit like you study, and you study, and then there's a course, and at the end there's an exam after 4 years, and you fail. That's not very helpful, right? So if you're an organism, then you would say, well, organisms have all these homeostatic variables that keep them from dying of hunger. Yes, that's very important. Getting too much sugar, pH value of the blood, and all these things. That's true. However, they are very different from organism to organism. They depend very much on the niche. And if you go to artificial agents, think of robots. You want to make a robot, you get a different robot, you have to design a different architecture. That the robot may be doing the same things. Think of humanoid robots. You have every type of humanoid robot has their own architecture and their own way of solving problems. And the question is, okay, this is really not very good to universalize. As evolution does not have somebody who sits there and tinkers with the variables, and people actually also underestimate how expensive the search in the big space is. Evolution is not that, it may be generous with bacteria, but if you have a look at cheetahs or other animals that are on the brink of extinction, it does not have the luxury to experiment too much. So the question is, does it have a more fundamental principle? And so many people have come up with a lot of interesting ideas to solve that. One of them is sitting just here. Pierre-Yves with his learning progress. There is, for example, predictive information. There are many other such notions. I don't have time to list them all. So I just wanted to mention that. And thank you, by the way, for inviting me to this fascinating conference. Here is the one that I'm going to present, and that is, we call it empowerment. And in a nutshell, if that's what you want to take away from the talk, and there's the only thing to take away, that's what you want to take away. Being in control of one's destiny is good. That's what you want. And you want something more. You want to know it. Okay? That's why we chose the word empowerment. We actually took it from social sciences. So the word was chosen specifically because it's not just about control, it's about knowing that you are in control. You need both. If you are in control but you don't know it, it does not count. So how does a formalism look like? I will make it very quickly. So again, we have our little agent here. We forget about the memory, and now we basically look at the following network. Let's assume I'm in state WT minus 3, and in this state I decide to inject an information A. A is a random variable, so I could choose anything that I can do with a certain probability. Then I wait a step, I inject a time T2, I wait a step, inject time 3, so I do 3 injections of information, and I look, okay, what did it do to the world? Yeah, so I do this, I do that, and I get a result. And now I can, of course, model that as a random process. And then I can ask, okay, what's the most information I can inject in these actions into the environment and actually see? I don't count anything I cannot see. I only count actions that have a visible, a sensor detectable outcome on the environment. So I maximize the potential future information flow. The potential, not what I'm actually doing. This is not what I do, this is what I could do. This quantity is a channel capacity in the language of information theory, and this quantity is what I want to maximize. So I want to go to states where this potential information flow is as high as possible. Think of it as a pseudo-utility. It's not a utility because you can't average it. It doesn't give you certainty equivalence. It's slightly different. But it's a pseudo-utility. You can use it as something where you want to go. So related concepts, just to get an idea, mobility in games. You are in a state. How many states can I reach from here in a given number of steps? That is a very useful concept in many games. So if you don't know anything about a game, having many options in the future is a good thing to have. You want that. Money is a classic, of course. We are here not far from Wall Street. And money, as you all know, is a potential. It's not, you can't eat it, you can't do anything with it directly, but you can turn it, you can convert it into options, right? Or rather, it's an option. It's an option that can be converted into a tangible value. Affordances, of course, that's the classic. Some things are easy to move. This is easy to move, well, with the handle, in principle at least. If you don't want to make it easy to move, so for example, some doors, I don't know which way to open it, what you do is you take away the handle on the side where you can't pull it. That's automatically an affordance that makes you not pull the door, okay? So pulling the door is afforded, or it invites an affordance when it's easy to do. Then in psychology, there's also a concept of perceivably different outcomes or efficiency divergence introduced by Österreich 79, graph centrality in graph transition graphs, and essentially you can see it as an antithesis to helplessness. I do believe that this is probably known here. If it's of interest, we can discuss it later. I want to give some examples. Forget all these three, let's just look at this example here. So basically you have a box in a grid world. That's the simplest of all examples. There's an agent. The agent can see where it is, and it can see where the box is. And now we have the agent can, in this grid world, take 5 steps. Basically, every step can be going north, east, south, or west, or stop. These are the 5 things, 5 options it has, and it does it for 5 times. And then you ask, what are the possible states it can reach? And to get an information value, a bit value, you take the logarithm. Okay? And so in other words, if the agent is on its own, it can just move everywhere the same number of steps. It has a certain range of operations that is roughly 61 states, and the logarithm of that is a little bit less than 6 bits, and that's empowerment in the free running agent. But if you are close to the box, you will see that close to the box there's a bump, and the bump is also almost 2 bits, because the agent cannot just move itself, it can also move the box. And it has 2 extra bits of the freedom to do so. So there's an automatic attraction to the box if you use empowerment maximization. Here's another example. I can't run the movie because it's not on my original computer, but I can explain what it's doing. So it's a Pac-Man with 3 particularly aggressive ghosts. They actually basically a clone of the most aggressive ghost types in Pac-Man. And when you run Pac-Man, you have to see that empowerment is a bit like a vitality measure. So when an agent dies, empowerment goes to 0. So automatically, you don't want to die as an agent. If you follow empowerment, you try not to die by default. And so this thing just tries to keep alive for as long as possible, but it has one more feature. It actually trolls the agents. It trolls the ghosts because it pulls them. It actually goes to the ghosts and tries to pull them behind it because that it controls it. So it's a bit trolling them. And this is an emergent phenomenon. We did not put that into the algorithm. It just comes out because it tries to control the environment. And that is also part of its survival strategy. Of course, it's not always a wise strategy. Sometimes it fails. But, you know, that is a limited time horizon. Before I go to the pendulum, I want to mention one more thing. We can also do the same thing with a kind of minesweeper, Minecraft type problem, and then the agent is being confronted with the lava poured in the world, and that agent starts building ditches or digging into the ground as to escape the lava. It really looks like these apocalyptic movies. Again, emergent property. We did not put that into the model. There was a mention of learning here. The pendulum swing up task can be learned on the fly. This model of empowerment needs a forward model, and the forward model is basically dynamics of the system, and it can be basically learned on the fly. This is basically showing the phase space of how the swing up task goes. The agent learns the dynamics of the system as it maximizes empowerment. And unlike in reinforcement learning, where you have to explore much more and you have to propagate everything back, everything is local here. It learns basically, this is the point where I'm trying to climb the grid of the world. I'll skip that one because I want to come to the last point. My time is running out. So empowerment is expensive to compute, has been expensive to compute. This has changed now. Especially for long time horizons and for systems continuous in time and space. And here I am showing you just the gist of a new approach that we have very recently submitted. And that's how it works. So essentially imagine a dynamical system and think of it continuous in time, but we discretize it in time. Don't worry, we can make the time as small as we want. So you have a dynamical system. Think of it a pendulum if you like. So this is a state, this is the next state. This is the uncontrolled system. So the state is transformed to the next state. And then there's a controller, this is the action. And here's a gain. The gain is just a linear parameter that changes from the state to state. So basically you can influence the system at each location a little bit. And essentially when you do that, you can, turns out there's a very simple trick. We haven't seen it all the years. Suddenly we saw it, in fact Stas saw it, Stas Jomkin, I'll give him a special credit for that, that you can compute it very easily what happens if you change the action on the effect on the outcome. So you can write it actually just as a product of the Jacobians of this function. It's quite easy to write down and a product of this gain here. And when you get these quantities, again, this is more just the gist of it for those who like to see the formalism. You get a matrix of different quantities, how they depend on each other. And this is here empowerment. This set of quantities actually corresponds to empowerment. This set of quantities corresponds to, yeah, I'm finishing in a sec. That's me, okay. Good. This one corresponds to a variant of a causal entropic forcing, which was introduced some years ago as a physical quantity of information, of intrinsic motivation. And this here is actually a well-known quantity in dynamical systems, namely the Lyapunov exponent, but only along the controlled degrees of freedom. So it's a measure of chaoticity, basically how far your pathways separate from each other. I will not go into detail how you use this to compute empowerment, but let me just say that you use them as a linear approximation from which you can get the empowerment quantity for this dynamical system. And the conclusion of what I want to say is that what you observe is when you maximize empowerment, this quantity, and in your path, what you're trying to actually walk is the critical Lyapunov paths, the places where the system is most unstable. But only when you can control it. You don't want to do that if you can't. Only when you can control it. And so the argument that many people have said that living organisms, intelligent organisms, seek the edge of chaos, we came to the conclusion we disagree with this. They don't seek the edge of chaos. They don't like the edge of chaos. You don't like standing on a limit of a cliff, unless you are, of course, a YouTuber who tries to make a movie. But actually, organisms want, if they use empowerment, if that's true, they want to become master of chaos. They want to be in charge of the Lyapunov exponents of the diverging trajectories. They want to get the control over them. So the bird's eye view is that agents separate the future, the potential futures, from confined causal pasts, the pasts that have happened. The futures are a potential. Empowerment maximizing agents minimize the commitment to a particular future. They always try to keep the future open if they can. But the point is, if we actually borrow a term from assembly theory by Sharma et al., that if agents are vessels for information that is basically controlling the environment, they are basically vessels for information that wants to be free. Because empowerment is about keeping your commitments about how you use the information in the future open. Thank you very much.
All right, fantastic talk and really cool to think about lots of problems. One thing I'm a bit missing is not all bits are created equal. So it seems like being satiated and not thirsty is also kind of a good goal to have before I can engage in this. So is there an idea how to combine these different motivations or?
Yes, first of all, the relevant information I talked about earlier is a way to actually distinguish bits for their value, right? So if you have a reward, you can do that. The second part where you can do something here is that empowerment depends on the sensor. So the sensor can be tuned, of course, to be relevant to the things you want to have, not the things you don't care about. So you can tune the sensor, and this is we are arguing that evolution does that actually. You can actually do sensor evolution experiments with empowerment, and it will prefer certain sensors as opposed to others. Of course, the question is always what is relevant to you. If you look at animals that have a limited capacity for time and space and can't do a lot of things, they don't need the full formalism here, but still a fly wants to be able to fly around, right? Even if it's not very interested in you know, learning about math or something. But you're completely right. If you have a particular goal that is dominant, that supersedes empowerment, and we have not. Our formalism does not yet look at how, well, we have some papers where we combine empowerment and explicit goals. I still I don't see a really clean way of saying, okay, this is when empowerment is converted into a concrete exploitation. So this is a work in progress.
Okay, thank you.
Hi, thank you very much for that talk. I like this, the whole framework that you put together, which kind of solves the problem of the black room where, you know, you don't just want to make sure you can predict the future, but you want to also diversify the range of possible future outcomes, right? So I think that's really nice that you can have both, know how to trade off. The trolling thing about the ghost really reminded me of my child, who's very happy to troll me and my husband and other children and his teachers. But there's bound to be individual differences, right? So there must be something other than just be a control freak and, you know, want to be a master of everybody and everything around you, like agreeableness. Maybe you want to be socially, you know, more cooperative, or you actually want to get some reward. We do, like, whether it's like food or something, yes, we want to stay alive as long as possible, but there are also more short-term rewards like getting food to eat, you know, or getting rest when you need it, or, you know, having a nice social interaction, so on and so forth. How do you build those things into your framework? And also, how do you model different individuals who might value these different long-term, short-term goals differently?
Okay, let's tease apart the aspects. So agreeableness is partly, you can make multiple agents with empowerment. We have done that, and we're working on that. It's relatively complicated to compute, but I think we're making progress. So being agreeable means that you have actually more empowerment in your social environment, because the bubble of autonomy of the different agents collide, right? If one agent is very aggressive, other agents will push back, because it's not a vacuum, right? You don't operate in a vacuum. In fact, if you have scenarios like autocracies or dictatorships, where the dictator can do what they want, they usually don't care being agreeable, and they don't care being socially acceptable. They can be they go as far as they can afford to do, right? So the fact that you are agreeable, or this is an advantage for you, is actually part of the formalism if you operate with multiple agents which have roughly the same bubble of autonomy. So I don't think that's too difficult to imagine that this can fit in. And let's face it, the empowerment formalism does not tell you who the agent is. So if you think of the agent as a football team, it's not the individual player that matters. So maybe the individual player wants to score a goal, but in fact, in good teams, the team wants to score. They will, even a top player will actually hand off the ball to a better positioned player that can score. So the identifying part of what the individual is, that is a problem that we have not solved. And it's not clear whether humans have a well-defined notion of that. Then sometimes you think, okay, we are here at this conference, we want to do this. Sometimes you think, I want to have now lunch. Sometimes you think, oh, New York, this is, so it really changes. Does it address, I think there was one question I missed of yours. Which one?
So the first part, we talked about multiple agents, right? But nevertheless, there are individual difference. Some people are more agreeable, have better social skills than others. So what would be different in your individual agents that will result in that kind of dynamics?
One thing you can distinguish very strongly are sensors. So for example, if your agent has no sensors for being rude, they may perceive themselves as being assertive when they just barge in on other people's personal space or something. So maybe the sensors are different. It may be also that their possibilities are different. They can't fine-tune how they interact with people, because that's also a skill, is an action. If you don't have the appropriate action set, you can not just look at individual actions, you can look at action sets, scripts that you're using. If you can't fine-tune them, then you just don't have this. You shouldn't be a diplomat, basically. And it's not the right way for you to put, but it may be the right thing to be in a, in an unpleasant environment.
I see. So, like, for example, if you have poor ability to identify people's internal emotional states because you don't process social cues well enough, that you don't even realize you made them upset, so that you can't control the environment in a positive way that you want, because you don't have the sensors to help you.
Exactly, or your actuators may be noisy.
Right, or but you don't have the skills to be able to affect them in a way that you like. Like you don't know how to behave. Yeah, okay, great. Thank you.
Thank you.
Okay. We'll take a last quick question and quick answer. Okay. Super interesting talk, Daniel, that I'm still wrapping my head around. Are you trying to discover an evolutionary basis for consciousness, or am I totally off base here?
Well, I would like, quick answer, yes, quick answer. I would like if I would say I try, I would like to say, I would lie if I would say I don't. But I don't understand consciousness well enough. So let's talk about agency. I think that's closer to what we do, agency.
Okay, thanks. Okay, thanks again.
We have now a 10 minutes break before the panel discussion. Okay. Oh Okay, so say hello to me. So what are you working on, Marcus?
So in general, it's like building
thing. I have no idea. But it kind of sounds, yeah. Group. All right, let's get back, guys. Yay. All right, come back in. Thank you to the organizers for bringing snacks. That was super helpful. All right, so here we are at the end of it all. I'm really happy that we ended with this 2 talks that gave really broad view of everything. And so what we thought we'd do in these hour and a half is try to put things together and sort of recapitulate what we've learned and see how each of us arranges it in their own narrative. So we have 3 presentations, so I'll start, and then Mark Dean will speak about how the view from economics, and Pierre Reeve will speak about the view from computer science, because they figured it all out. And right, no pressure. It's like it's obvious. All right, and this maybe should take like half an hour or so, and then all the organizers will get up there, but we'll open things up for discussion, and we don't mean it that you guys ask questions to us. We're just there to stimulate discussion, and you ask questions from the speakers, and the speaker asks questions from the students, and so on. So we will circulate with the microphones, and you were just there to help unstick the conversation if it gets stuck. Okay, so let me start. So because I'm a card-carrying neuroscientist, I'll talk about the brain. Okay, so my absolute favorite thing about this field and this topic is that it frees us from this tyranny of the bottom-up idea that we've lived with in neuroscience, in other fields as well, but in neuroscience, I just feel it's like strangling. So the idea is the world is there's an image, and then it drives you, and it registers on your brain, and then you do stuff based on it. And this stuff works. It works fine if you're in a toy world like the laboratory, where there is this amazing power to curate your input and select it. And then it totally breaks down the moment you see a real life input, and becomes obvious how insufficient this idea is. So in this input, you have to start from the center. I need Waldo. I expect Waldo to be there. I will do something with Waldo. I will get something from Waldo. All that cognition has to come first and tell the eye to move and find Waldo. And only after the eye finds Waldo can I do what we've been talking about. Okay. So what does this tell us? Okay, so I'm gonna, I just worked on this starting at 5 this morning, so it's gonna be a bit messy. So what does this tell us? I'm going to try to think about like a couple of lessons and then just move to questions that kind of stuck in my mind over these 2 days. So first of all, it tells us about the incredible primacy of visual search, right? It's just essential for survival. And we've seen in Joy Geng's talk about, so we've been looking at search as just the mechanics. Once you know the target, how do you find it? That's the focus question that people working on attention have looked at. But I think now we're trying to look at, there's so much more cognition behind visual search. How do we select the target? That is a huge, complicated question. And then how selecting the target alters how you encode and remember the target. It really depends, how you see it depends on what you want to do with it. Okay, what is my one lesson? Okay, the one lesson that I wanted to bring up that, that I've been thinking about is this question about different kinds of actions that we have available to us and the purpose or the telos of each action. And so a lot of things that what we do are skeletal actions. We move our effectors and we move the muscles. And I would argue that the telos of these actions is to act on the world, to exert force on the world. And it is only in this way that we can acquire rewards that we need for survival. We have to eat, we have to drink, we have to speak, everything, all the necessary biological rewards, we have to exert some sort of force. Now, the skeletal actions do other things too. They also gather information. So when I grab something, I also feel what it is. We have sensors in our skeleton, and they also communicate internal states to others, our goals and intentions. But I would argue that those maybe are a bit secondary goal, and the main goal of a skeletal action is to exert force. On the other hand, you have other actions, such as making an eye movement, turning your head to listen to something, sniffing to get an odor. Sniffing is a bit more complex because you also need it for breathing, but let's just say that. And those actions do not exert force on the world. They do nothing to the external world. And they only are there. Their telos is to alter our internal state. And these actions have, they do have another role in social situations, is to communicate our internal state to others by communicating where we're attending, for example. Or you can even affect another person by looking at them sternly. You can get them to do stuff, or even your pet dog. But outside of these social situations, I would argue that the telos of those actions is to change your internal state. Okay, so I think we've really heard really beautiful expressions of this principle. We don't talk about it, and I often wanted to write about it, and I realized I don't have words because nobody's talking about these ideas in neuroscience. It's pretty obvious, but we heard, I was so happy to see Bruno Overbeck's result that if you do exactly the same task with an eye movement or an arm movement, you have a different behavior. And I think that I would trace it back to the fact that the eyes are more exploratory because that's what they're there to do. We heard in Matthias Gruber, I hope I understood that correctly, but when you quantify the entropy of where people walk versus where they look, they are different measures, right? They mean different things. They have different correlates. And finally, we heard from Johann Triesch how how we control eye and hand, and I think that's the sensing component of the hand. It can not only control our immediate mental state, but how we represent information, how we put together those incredible visual representations that we have, like about object categories, about oriented lines and segments and what have you in the visual cortex that nobody knows why they are the way they are. They are probably also actively controlled by the sensing type of actions that we do. All right. And okay, so this is my caution. So my caution is to neuroscientists who use various effectors in order to understand neural activity, right? And in a sense, the eye is a favorite effector because it's so easy to train and so easy to measure. In effect, there's a hidden danger there because people have used the eye as a proxy, as a stand-in for a decision, right? So in a decision task, you give a signal to your animal, and then you train the animal, look right if you think the signal is that, and look left if you think it's a different signal. And what you're doing here is the eye does not explore anything. You have co-opted the eye in order to act on the world, basically, in order to get a reward. And so so this is different from how we use the eyes to explore. And the key is that when you start to interpret the neural activity related to that, it can really lead you astray because the computations are very different. The assumptions you make are very different. In this co-opted artificial task, the eye reacts to information that is given to it. The eye simply reports the endpoint of a decision. And also, and very concretely, the prediction is that I'm going to move to the target that is the most certain, where you have, so if your posterior is maximal, let's say that the correct target is on the right, the idea is I'm going to pay attention to that region of maximal certainty and go there. And, right? Whereas if you have the eye as an exploratory mechanism, you make very different prediction. The eye doesn't react to given information, it looks for information. It doesn't just report the endpoint of a decision, it creates the decision, it's in the middle of the decision-making process. And very concretely, you wouldn't think that you would look at an item that you know with certainty. That's ridiculous, that's redundant. If you know it, you wouldn't look there. You would look at an item with the highest uncertainty in order to resolve it. So this really, I mean, some of you may know that people who look at decision making and someone like me who looks at information seeking have been recorded the same neurons over decades, and we find inconsistent results. And everybody is like going crazy and everybody hates this particular area. And I would argue that this is the reason, you know, and we have to be a bit more careful about that. All right. So, all right, okay, so now, so that was my lesson. So now let's talk about 3 questions that I saw. Okay, the dilemma of bad news, right? What does the brain do with information that we don't like? And we've seen this come up over and over and over and over, right? We go into the woods and we see a tiger. That's no good. There's a big conflict there, and we've seen that this bad kind of information does many things. So it can skew information search. You may not look for the most, you may avoid information. You may rather be in the dark. It has consequences for explore, exploit, for information seeking decision, the correlates, the neural correlates of it, like Ilya spoke. There's, you know, it probably plays into things like risk ambiguity or preference, avoidance, novelty seeking or avoidance. And then there's this, weird thing that we avoid bad news perhaps about ourselves, but we love bad news about other people or about other things, right? There's a lot of stuff. You know, art is all about sad and scary situations. Okay, so there's a bit of a dilemma. Okay, so where does this come from? So we really think, I mean, I hope this isn't too obvious, but we really think that this is very fundamental to life. So not just brains, any life like an amoeba. It's basically an approach avoidance machine, right? So amoeba has to find good things and go there and detect bad things and avoid them, right? And then, and let's see, and what happens? So let's say even a slightly more complex organism like a frog, it has to approach the food. And what happens when the frog approaches the food in order to act on it and eat it? Well, it also learns about it because it attends to it. Because in simple organisms, attention and action are very closely aligned. So you attend to this fly and you learn about it and you represent it better. But what happens if you have to avoid an enemy? Well, you need to detect it, but not too much, because then you go and hide. So you don't need to know the details. You just need to know a little bit that it's there, so then you can ignore it. So you learn less about stuff, you learn more about stuff you like and less about stuff you dislike. Okay, now in people, we have evolved, right? And we're not so stimulus bound or goal oriented like a frog. We can do things like, you know, talk to our enemy in order to understand them better, right? Or even something simple like when we cross the street, our goal is over there, but we don't have to look over there. We can look up at the traffic light, get a symbol, and then orient to our goal, right? So we partially decoupled information gathering from the goal. But still, we can't totally decouple it, right? Because our information gathering eventually has to be adaptive, so it has to lead to some goal, even if it's on a more distant timescale. So we haven't fully resolved this conflict, which means that, just to remind you, information seeking is biased. And whenever people say information seeking is biased, the next sentence tends to be, oh yeah, there's the stupid people who believe in quantum and whatever. They don't know what good information is, but that's not the point. It has to be biased. Even the smartest of us, even Nobel Prize winners, are biased simply because the world is infinite and we need a bias in order to survive, right? So just remember that, a bit of humility. Okay. So first point was bad news. Second point is mechanisms of control. Okay. So I should have started the other way around. We heard from Matthias today about appraisal, right? Again, just because there's too much information, there's too much uncertainty, we cannot resolve it all. We have to decide, is it worth to me to resolve the uncertainty or not? We need appraisal mechanisms, and those mechanisms will implement something like cognitive rationality that economists will talk about. We need to titrate our cognitive resources. We have a model of cognitive control that involves the anterior cingulate cortex. It's a super simple-minded and simplistic model that we're working on. So the idea is anterior cingulate receives reward input from dopamine neurons, also intrinsic rewards related to reducing uncertainty, like Ethan has shown. And if it detects a need for control, a drop in reward rates, it basically tells the brain, hey, wake up, you need to do better. It calls for a boost of norepinephrine. Norepinephrine goes to other parts of the brain, like the parietal cortex or the visual system, and improves processing in some way. But norepinephrine is a cost, right? So for some reason, the brain doesn't want to release too much norepinephrine. We don't know what that is, but we just assume that that's the case. And so it will only be released if there is a benefit, some foreseeable benefit. Again, it could be in terms of reward rates or in terms of reducing uncertainty or what have you. So this is our very rough hypothesis now of cognitive rationality. As you've heard, that there are a ton of questions here. For example, Matthias put this appraisal process in the lateral prefrontal cortex. We put it in the ACC. Who knows? None of us knows exactly where it is. But at least it's a testable hypothesis. And this is a biological circuit that implements this high-level thing of cognitive rationality, how the brain self-regulates its internal state. Okay. Okay, so I mentioned how Matthias relates to this. And another theme that we've heard that relates to this a lot is this idea of stress tolerance and uncertainty attitudes, right? So you want to detect uncertainty and you want to approach it in a sense, but uncertainty is not, the brain tries to avoid uncertainty. So, you know, an entropy signal, an uncertainty signal is very closely related to an anxiety signal, as a distress. So we're ambivalent about uncertainty, whether we like it, whether we want to resolve it, and so on. So we've seen, Catherine Hartley talks about how it develops, maybe even in a nonlinear way. Matthias talked about the relation with stress tolerance, and then Ifat talked about all about uncertainty and how that relates to psychiatric disease. Okay. And the last topic is, I just wanted to talk about these questions of these terms of curiosity and information seeking that we've heard about and we kind of use interchangeably, but are they the same thing? All right, so here I just want to mention a study that we did, and it's in collaboration with many people who are in this room. What we did is we did an online battery of tasks, and we implemented 9 information-seeking tasks. You can't see here, it doesn't really matter, but they're contributed by individual labs that we collaborated with. So these are little tasks that we came up with, each on our own, individually. So we had people do all these tasks online, we parameterized them, and then we did a principal component analysis of the parameters, and we found a first principal component that captures something like the distinction between uncertainty-driven and random exploration. And this is the distinction that Berline started, specific and diversive exploration. So that's really cool. So at one end of the principal component are parameters that tell us to what extent participants explore in what would be normative in these tasks to reduce uncertainty. And at the other end is how they explore in a non-normative way to do something else, in particular randomness. Okay, and then, so this is the view of curiosity that as we imagine it in the laboratory. And then we took personality questionnaires, and we took the key, a curiosity questionnaire, of course, but also the Big Five and some other questionnaires. And we said, how well can all these personality traits predict this principal component across individual participants? And we find they can predict it pretty well. So we have a correlation there of 0.44, which is, pretty acceptable. Is better than a random model. Okay, but now let's look at which individual traits predict that exploration axis. And the first striking thing is that it's not curiosity or openness to experience. It's not that. Those are the weights of prediction. Those things are right in the middle. Not good. Okay. What are other better predictors? Need for cognition was right here. So yay, Kinneret. Okay. The next set are stress tolerance. Is a positive predictor. The more stress tolerant you are, the more you will embrace uncertainty and seek to reduce it. Thrill seeking, on the other hand, is a negative predictor. Okay, so how do we interpret that? We interpret it to say that if you have more tolerance to stress, you will approach uncertainty in order to resolve it. And also you may not like to be thrilled, meaning to be hit by an unexpected error, right? So thrill seeking means risk seeking without knowing things in advance. And this is supported by this other thing, which is BIS, the BIS, which is here, which is a positive predictor, which also means people who are higher on the BIS score just hate errors. They want to be error avoidant, okay? So the bottom line is that the information seeking task that we came up with independently in our labs, maybe because all the scientists think alike, I don't know. But they do capture something significant about attitudes toward uncertainty, how we approach it, how we explore based on it, and also cognitive processing, the cognitive load of knowing how to explore and how to resolve uncertainty. That's not trivial, right? So these talks by Ifat and Matthias and Kinneret got to that. Okay, so what is missing? Why don't we capture this curiosity construct? Okay, so I have no idea, but here's my hypothesis. And that lies in this last predictor, which was actually our strongest predictor of curiosity, and that is extroversion. Okay, extroversion is a super broad construct, so this is very speculative what I'm going to say now. And extroversion was a negative predictor, meaning that people who are more introverted, less extroverted, will be more focused on reducing uncertainty, will have more directed, cognitive-heavy style of exploration. And so my thinking was that these people who are more introverted, they just like to think more, they're just more thoughtful. They don't go around asking all kinds of silly questions. They just sit in their room and they talk and they think by themselves, and it's like that. So I was so happy that, like somebody said, then you read some paper and you find something that supports your hypothesis. So I was so happy that Jessica provided that, because she told us that people who are more curious, they like to be alone. At least that's what I understood. I hope I didn't overinterpret that. So I thought that was amazing. And then she also kind of suggested, she and the other talks on creativity suggested why they might like to be alone, because they have richer associative processing. they don't feel alone because they talk to themselves all the time, you know, so they keep themselves entertained and they're less bored, right? So, all right. So then this leads to another prediction, is that curiosity really involves interaction with this rich knowledge base and semantic content. And this is something that we do not capture in our really pared down, abstracted information seeking task. So we need to really, if we want to understand curiosity, we got to get to those rich, meaningful, real world situations. And so I was so happy to see all these tasks that start looking at real world situations in ways that are understandable and quantifiable. Because of course, people have looked at spontaneous behavior for decades, but if you don't have a hypothesis, you don't know what you're looking at. So, Matthias' task and Kate Hartley's task that are content rich, I think are going to be just really super important. Okay, and the last thing which I think is related to this, but it's a very specific query that I had. So if you think about this concept of information prediction error, which is something that happens after you receive the information, right? So you have a certain expectancy, and then you get the information, and then you evaluate it. So there's something like information prediction error. And it strikes me that we have at least 3 definitions across us of information prediction error. So I think Tali Sharod with in her paper with Ethan, it defines it as whether the information reduces uncertainty or not, right? So it's again very simple task. You could either get a signal about what the reward you will get in a few seconds, or not get a signal. So that's it. So, and that type of error is useful to tell you whether a source of information is good, right? Will that source of information give me what I need or not? Because if it doesn't, I should not attend to it anymore. But then Matthias tells us something completely different. And he says information prediction error is how much something triggered my imagination. Like, what is that? Right, in terms of uncertainty, right? It's a whole different thing. And then we heard from Flores Delange, there's something like surprise. When I get information, I could be getting what I expected or something that I did not expect. So how much conflict with expectations do I have? So how do these 3 relate to each other? We're going to have to start, agreeing on them. Okay, so I'm sorry, I went over time. So it's time for me to give the floor to Mark.
Before you go, tell me how to use this.
Yeah, down, advance.
Down.
And then the circle is the point, laser point.
Okay, hello everyone. So I'm Mark. I'm from the economics department here at Columbia. So let me get some caveats in first. So first of all, I mean, as a sort of a little bit of an outsider, I found this an incredibly interesting and stimulating conference. And I think there's a lot for not just me, but for economists to learn from the type of work that's being done in this room. But having said that, I am a little bit of an outsider here. So many of these talks were not in my wheelhouse. So it's possible that some of these questions and comments are going to be a little bit naive. So I apologize for that in advance. All I can say is that I think the answers to some of the questions that I'm going to ask would be of interest at least to the median economist, or whatever I am, slightly below median economist. So these are things that we would like to know. And basically, I'm going to cover 2 main issues. The first of which is operational definitions of complexity and creativity. And this is going to be sort of a plea for help, because this is something that I think we could really do with. And the second thing is going to be something a little bit more speculative on the motivations for information gathering, and some of which we've talked about. Along with the economists, I've been extremely paranoid about the lack of pictures in my slides. It's not something we do. So I couldn't think of any helpful pictures at all. But it is true that my football team, Sheffield Wednesday, was involved in one of the best games of football in recorded memory last week. So I'm just going to put a couple of pictures of Sheffield Wednesday in the corner. If anyone wants to talk about this offline, I'm happy to do so for hours. Okay. So first of all, I wanted to talk a little bit about creativity and complexity. So two of the things that were in the title of the conference. So I think these are both things that most economists would agree are important and things that we would like to be including in our models, but that we don't necessarily have a great handle on. So thinking first about creativity. So there is a little bit of work on thinking about creativity in an economic context. And it says things like, well, maybe we can think of creativity as a form of human capital. You know, if you learn to be more creative, then that's going to make you a better employee. But there's not a lot in our literature which tells us about how to differentiate creativity from other forms of human capital. Similarly, you know, industries that we call creative industries are hugely important. They count by, you know, one measure that I stole off the internet. It's about 6% of global GDP. So clearly understanding, we have definitions of what creative industries are, but we don't really necessarily have models that tell us how to treat creative industries as different from, you know, fishmongers or other types of industry. And similarly, it's agreed that creativity may be an important driver of technological innovation. So, you know, if we want economies to grow, then one of the ways that happens is through technological innovation. And creativity is potentially an important driver of that. But again, there's no sense of knowing thinking about creativity as separate or distinct from other models, other forms of research and development. So in fact, you know, this is not actually something I work on hugely, so I did a sort of literature trawl, and one of the things I found was this article from 2010 by an economist, a very grumpy article, where he was looking at how creativity changes over the life cycle and saying, this is going to be the article that, you know, it means that economists are now going to have to pay attention seriously to creativity. It's published in 2010, it's so far got 36 sites, so he's not started the revolution that he hoped to, but I think that, you know, there's clearly something important here. Similarly, if we think about complexity, this is closer to stuff I know about. And, you know, I work in bounded rationality, and it's long been understood that complexity may be a limiting factor in economic decision-making, something we should really be paying attention to when we think about bounded rationality. But our approaches to try and understand or measure or quantify complexity have been pretty scattergun. So in a repeated game settings, we thought about finite state automata, and you use that as a measure of complexity for strategy. So maybe people are limited in the sort of the complexity of the strategy they can use. In static games, we have this idea of level K, so the number of steps of reasoning required to implement a strategy. So again, that's been used as a measure of complexity. There's recent work by, in fact, someone who's on the job market this year thinking about choice between lotteries, where they used the size of the support of a lottery, so the number of different prizes as a measure of complexity of that lottery. So, you know, these all feel like they're capturing something, but I don't think anyone's going to the mat and saying, no, we've nailed it. This is exactly how we should think about complexity. So my first and very basic point is just thinking of myself as a consumer of the stuff that we've learned about in this conference. If you guys had better definitions of creativity and complexity, then that would be incredibly useful for us. Sorry, I mean better than ours, not better than the ones I've heard. The ones I heard were great. So for example, thinking first about creativity, is there a working sort of behavioral definition of creativity that we could steal and we could work on? So some of the talks have, as I understand them, have described measures of creativity that are used in the literature. So things like the number of uses you can come up with a coin, or the number of animals you can think of in 3 minutes, and stuff like that. One of the things I don't know as an outsider is that, you know, are these well validated in the sense that they separate creativity from other things like memory or intelligence? And is there something close to a sort of operational definition along the lines of what we have for risk aversion? So the idea that, you know, we measure risk aversion as the distinction between certainty equivalence and the value of a lottery, or temptation, where in econ this has been operationalized by demand for commitment. Is there something along the lines that we can, are we close to having something like that for creativity? And if so, then maybe this would allow us to sort of start putting creativity into our models in a way that's different from just having another form of human capital, which we happen to label creativity. Similarly, are there definitions or notions of complexity that we could steal? So again, I mentioned that this is an issue that's dogged research in bounded rationality for a while, I think. One approach that might be interesting going the other way, for those of you who are interested in complexity, there's a recent paper by Preya, who's taken a revealed preference approach to complexity. So in this case, what he does is he basically gets people to implement different types of algorithm and then asks them, how much would I have to pay you not to do that again? Or how much would you pay me, sorry, to not do that again? So using a sort of revealed preference approach to understanding what people do in fact find complex or not. So that's been useful, but of course the space of possible things that we could attach this complexity measure to is enormous. And so without some guidance, we can take lots of revealed preference measures, but it doesn't really help us in coming up with a theory. So anything you've got on this would be very useful for us as well. So that's my sort of my cheap shot plea for help. For the last few minutes, I wanted to talk a little bit more about this notion of curiosity and the idea of information acquisition more generally. So from the economic side, these are issues that we've thought about a bit, and I just said that there are two broad classes of models that suck up most of the attention here. One of which, and probably our favorite, are models of instrumental information. So this is something we've all talked about. So information is valuable because it's going to allow us to make better choices down the line. So this is something that we've thought about since the 60s. I've done some work on this. In terms of this conference, in the economic section, this is Pietro's talk was right in this vein. On the other hand, we've got models for preference for early or perhaps one-shot resolution of uncertainty. So these go back to the 70s with Krebs and Porteous. Andrew, who's my PhD advisor, worked on this in 2001. And these are sort of distinct and models of instrumental value of information in the sense that your preference for information here or your preference for timing of information really comes about from the shape of your utility function. There's something you like about the information. And in fact, one of the things that's been worked out in the econ literature is the link between unexpected utility theory and reference dependence and value for either typically one-shot resolution of uncertainty. So this is the type of thing that I think here has been more represented by the work of Yusuf, Sharot, and various other talks. Also a shout out that, there is a literature on the consumption value of information. Either you like to hold views that make you feel good or the suspense and surprise stuff. So this is what Michaela talked about in her talk. I'm actually going to push that off to one side because I couldn't shoehorn it into my thesis. So I'm just going to forget about it for a while. So one of the interesting things from my point of view is that, in this conference, there's been this sort of wealth of other possible motivations for information gathering that have been discussed. So, in fact, this slide is out of date given what I learned about this morning, but things like curiosity, novelty. So curiosity, I think Russell defined this as, a utility simply from the change of your beliefs. Novelty seeking, so a preference for stuff simply because it's new. Uncertainty reduction, which is obviously something that Jackie's lab has worked on a lot. And then I think the talks this morning listed a bunch of other possible motivations for information reduction. So the slightly naive question I wanted to ask, just to finish off really, is whether should we think of, here I've listed 6 possible distinct sort of motivations for information gathering. Should we think of these as really being 6 distinct drivers of information demand, 6 different reasons why you want information? Or could we instead think of them as being 6 different strategies for obtaining the right amount of instrumental information? So instrumental information is the only game in town, but sometimes we need other strategies to help us drive towards this. And I think that the talks today suggested that this is something that people have thought about quite a lot already. So the view I wanted to take is that the ultimate goal of an organism is given. We know what it is. This is the type of bullet point that makes me extremely nervous to put on in an audience of actual scientists. But let's say it's something like maximize evolutionary fitness. So we know what the ultimate goal of the system is, and what we think that the organism is trying to do is choose the right amount of information in order to maximize that goal. So the way that economists would usually formulate that as a problem, as a rational inattention problem, and I'm sure there are equivalents in psychology and neuroscience, is you've got a set of states, you've got a set of possible actions, you've got a utility of each action in each state, which you know. You can choose amongst one of a bunch of different information structures, and the value of the information structure is the expected value of the optimal actions taken at the receipt of each signal. And so then when you choose the optimal information structure by choosing the one that maximizes this value net of cost. So this is a sort of typical instrumental information setup. So the point, which is, I think, very underexplored within econ, though it sounds like from the talks today, people have been, there's lots of work on this that I should now pay attention to outside econ, is that this approach quickly becomes completely intractable. So calculating this value of information quickly becomes an impossible task. So for example, how would you calculate the instrumental value of attending this conference? What are the states? What are the signals? What are the actions one would take after the receipt of this information? What are the utilities of those actions? Seems very hard to think that that's what we can do. And this is only going to get harder if we add additional complicating ingredients that people have mentioned in various talks. For example, Ming's lovely talk on open-ended decisions, where we don't even know how to conceptualize the problem. Adding an explore-exploit motive makes all of this much harder. So again, type of bullet point that makes me nervous, but arguably organisms can't literally be solving these problems, either implicitly or explicitly. So maybe what we've evolved is a bunch of heuristics or strategies that allow for good approximate solutions to these problems. So for example, there is on average some value to exploring novel things, even if I can't calculate this exact value. There is on average some value to reducing uncertainty, even if I don't know what it is. So things like curiosity, novelty seeking, uncertainty reduction are really just approximate ways to value information when you don't know or you can't calculate the true value of this information. So what about things like preference for early resolution of uncertainty, a la Yusuf's talk? Well, I mean, this seems to be a problem for this idea in that these experiments are designed to have literally zero instrumental value of information. So why would you pay to have this information earlier? What's going on? Well, one possible reason is that these are situations in which information literally has zero value are extremely rare. And so that strategies that are generally adaptive work badly in this specific setting. So for example, if you're a hyena wandering around the plains of the savannah, maybe it's very valuable for you to know 2 minutes before everyone else where the reward is. So this is something that Ethan has talked to me about when I collared him at one point in the conference. So that's a possibility. I mean, the last thing I wanted to say is, well, how can we stop this? Of course, I can say these things and, maybe you find it plausible, maybe you don't, but how can you stop this from being a just so story? Well, one possibility that came to mind is whether we could steal an approach from economics, which economics previously stole from perceptual psychology, and imagine that what's going on is that we have a Bayesian decision maker who gets noisy signals about the value of information in a given setting. So we have a prior about the value of information, and then in any given setting, we get an unbiased but noisy signal about the value of information in this particular setting. So what does that mean? Well, on average, what we do is value the information as a weighted average between the mean, the prior, and the true value. So what does that mean? It means that if we look at states in which information has a low true value, then we should see it to be overvalued. When we look at states in which information has a high true value, it should be undervalued. So could we test this? Well, potentially what we could do, and maybe someone has already done this, is take a paradigm like Yusuf's, or some of the similar work in monkeys and rodents, and vary the true value of information. For example, maybe there's some probability that the reward will disappear unless you get some advanced information and you can claim it. And then what we might hope to see is some sort of pattern like this. Oh, sorry, the 45-degree line is effectively invisible, but there's a sort of 45-degree line. And what we want to see is that the true value, the perceived value responds less than 1-to-1 for the true value. So when information is very unvaluable, you overvalue it, and when it's very valuable, you undervalue it. So this is the very final thing I wanted to say, is that this is an approach that has been used recently in sort of behavioral economics to study similar problems. So, for example, Dan Benjamin, in a 2019 paper, this is a survey of how people respond to signals, and he says that most of the evidence suggests that people overreact to signals, underreact to signals, but sometimes they overreact. So why is this? Well, a recent paper by Ned Overgenblick and various others have suggested is that maybe people only have a noisy understanding of the signal strength. So the similar sort of setting, you have some prior about how strong, how informative signals are, and then you receive some sort of noisy information about that. And that, again, that would see you overreact to weak signals and underreact to strong signals. And indeed, that's exactly what they say. So this is, this is actual signal strength along the bottom, perceived signal strength along the side. And this is something that is being applied to a bunch of different settings in econ recently. So, you know, for what it's worth, my thought is whether a similar approach would be useful here, that you have some noisy understanding about the value of information in any given situation, and that can lead to some of the patterns that we described. That's it. Thank you very much.
So now let's speak about the AI perspective. So just before the AI perspective, I'd like to say a few words of thanks. So at the beginning of the week, Jacqueline thanks the local organizing team who did an amazing work, and that's really true. And so thanks to them. But also Jacqueline assembled a group of co-organizers. But I think it's pretty fair to say that, at least for me, the contribution was very small compared to what Jacqueline did. And so I'd like that we all make a clap to Jacqueline, because that's amazing. Okay, so Jacqueline said that computer scientists figured everything out. I don't think I really agree. But I think that computer science and AI is a good way to open perspectives. And I'd like to illustrate that discussing a few examples we've seen in various talks and various posters during the conference. Okay. The first perspective is one that was mentioned actually in Ben Hayden's talk. He was remarking that engineers begin to actually use curiosity to solve engineering problems. And this has begun to be the case in a few years ago in machine learning, like people were using those video games as some kind of benchmark for evaluating the power of various machine learning algorithms, like reinforcement learning algorithms. And some of these games were very difficult to solve, especially because they were games where the reward or to get a non-zero score was very, very sparse. And basic reinforcement learning algorithms, well, or even not so basic, for example, such as the one called AlphaGo, the one who bets the best players in the world at the game of Go. If you would use them in this kind of video game, they would perform very poorly, because when they don't get a few examples of reward, what they do is they just move around randomly. And when the world is complicated, moving around randomly makes it very unlikely that you end up finding by chance a reward. In the game of Go, they get a lot of reward because in the beginning, they begin by playing against other dumb players, and half of the time they win. And so, I mean, they get a lot of win. And so that's a lot of information. Here, if you just play randomly in the game, you win nowhere. And actually, this example is now completely mainstream in the machine learning literature, and it's not only for video game. For example, in my team and many other teams in the world also, we've been using curiosity to solve difficult engineering problems in the domain of robotics. So, for example, here, okay, everyone needs to play the game and. Okay, second button, okay. So here, for example, you have some humanoid robots, and in front of them there are a number of objects. So actually, maybe you don't see well here, but they know basically nothing about their environment in the beginning. And in their environment, there are objects like their hand, which they can see, and is one object among others. There are joysticks, and actually just in front of here, there is an object like this, which is kind of a playground where there are objects they can move, and those joysticks actually control one of those little robots, like remote control robots that can be used actually to push the ball around. Here you see better on the robot on the back. Sorry, I didn't take the right photo. And then maybe the engineer wants that the robot learns to do a movement that's going to push the yellow ball forward. And the movement basically requires to actually push only one of the two joysticks controlling those little white robots to move the white robot around so that it's going to move the ball and to push it in the right direction. And if you use AlphaGo for this, you can wait 1 million years, it will never solve it. On the opposite, if you build a system and you don't say to the robot that this goal is particularly interesting, but you can tell them like generate your own goals. Like it's a form of exploration I'm going to talk in the last slide, which we call autotelic exploration. Those robots, they can invent their own goals in a vast space of goals, their own problems, and they are going to organize as they wish in that space. By following actually goals that maximize learning progress, which is another idea I'm going to discuss quickly. Actually, in just a few hours, in the physical robot without any simulator and any supercomputer, the robot ends up finding one way to move the ball around, as well as one way to move other objects around. And this was really very, very efficient. And so what this tells us is that now we know very well in engineering that putting curiosity in a learning algorithm is going to help solve complicated problems. And I think this can open a perspective that's very related to what Mark said before, which is like hypothesis of why in evolution organisms may have evolved mechanisms, various kinds of mechanisms of curative exploration. So if you replace the particular engineering problems of moving the ball around by finding food, and this human in robot may be an animal, and maybe it is in an environment where finding food is very difficult, and where the environment is changing all the time. So when you found it one time, you cannot like pass the genes to the next generation so that they can know in hardware where to find it again. So in this kind of environment, actually, what's best if you need food to survive and food is hard to find, the best is to forget about the food and explore intelligently the environment. And this will maximize the probability you actually find the food as a side effect of that. If you only care for the food and you say it's very important and everything else I don't care, then you will die. And that's a very important lesson that now engineers learn, and I think it gives ideas about evolution. Okay, here is a very different perspective that AI can provide, which I think was illustrated by the talk by Floris Delange. Something that's very, very important, I think, in the future of research and curiosity, and that was well explained by Floris, is how we can move to study this in more naturalistic settings. Of course, it's not so easy in the end to study curiosity in the lab, because even if you're like letting people and children in a room and they are free to do whatever they want, they are still in a lab and they are not going to behave the same way as they do in their homes. So field studies to study curiosity are going to be very, very important in the future, but then this is posing very difficult methodological issues, especially, for example, if we have theories of curiosity we'd like to test, and for example, they might involve ideas like the brain is going to like things that are novel or surprising. If we want to be able to interpret the behavior, it's important we have an idea of what actually the brain in the naturalistic complex setting believes is novel or surprising, etc. In the lab, we can have ways to control things that probably they've never seen in the past, and so we can be pretty sure it's going to be novel and surprising to them. In the wild, it's very, very difficult. And so that is the reason why Floris proposed that maybe, for example, AI models like the big foundation models, like language models, visual models, could be used to help a little bit, because they were trained on so many text and data set of images that they know what's in average very frequent or very rare in the real world. And this could be used in principle as a proxy to estimate whether something a child is exploring is something that's pretty novel or not. But of course, there is a challenge, because this is a measure of novelty that is kind of an average over a very large data set that is basically also much larger than what the child has seen in his life so far, even an adult. And it's actually not measuring subjective novelty, like or subjective surprisal, which is like for this particular individual who has a particular history and a particular representation of the world, it's actually not sure that something that's very novel from the perspective of a language model is novel for that child and vice versa. And so what could we do? I mean, this is actually posing interesting AI challenges, like how could we maybe leverage incremental learning version of those large models and like give them access to data from particular individuals. Actually, there are labs right now in the world which has become to collect multimodal data of children growing in houses, like in their natural houses, and they're collecting thousands of hours to have data sets covering months and years of development. And when we have this, maybe we can actually have something like training those models on the history of what they've seen and have a good proxy of what their brain is going to find novel or surprising or whatever. Another topic, another perspective we've seen is, and it was well highlighted yesterday by Rentri's talk, is the idea that beyond considering curiosity in terms of the behavior it generates and in terms of the efficiency and the performances it leads to in terms of solving downstream tasks, external tasks that maybe later appear. It's also very important to understand how curiosity organizes exploration in a way that's going to bias internal representations that are learned by the brain, may it be artificial or a natural one. We've seen yesterday with Joran that the way one is behaving, exploring, collecting data leads to data that has a very particular structure, and the structure of this data in turn is going to influence very importantly the structure of internal world models. And I believe that this is an area which is very, very unexplored. There is really a lot to do, especially from the perspective of the role of curiosity in building internal representations. Another perspective that AI can provide also is more the formal perspective, like trying to define extremely precisely and mathematically concepts, and maybe highlight that for things like uncertainty, for example, as we saw yesterday in the talk of Ian Husband, when we talk about it, like maybe this week in informal conversation, we use one word, but actually there are many different kinds of uncertainties. And one important difference, for example, is between aleatoric and epistemic uncertainty. And I thought the talk of Ian was very, very insightful for explaining that, and also for showing that there are relatively simple computational mechanisms that can, in certain contexts, make the difference between the two. But then one question is, do human brains make actually that difference that we can make from a mathematical perspective? And also something that we've not so much discussed, I think, this week during the talk of Ian, but in many other talks, is the difference between objective uncertainty, which is the uncertainty measured from the perspective of a scientist observing the scene, who has all the mathematical tools at his disposition, versus subjective uncertainty and even subjective epistemic uncertainty. Maybe the brain sometime, because of some biases, may estimate that there is a high level of epistemic uncertainty in a given situation, and he may be completely wrong. So for example, there are many cases of experiments where people actually believe there is structure when there is only noise. And actually, in an experiment we did with Jacqueline a few years ago, we were presenting different tasks to people, some of them very easy to learn, some learnable but complicated, and some of them completely unlearnable. And I was really aleatoric uncertainty here. And there was a significant fraction of people who would spend a lot of time with the aleatoric task, and they were really convinced there was something to learn. And so how does the brain work in that case? Like, probably actually they are not interested in aleatoric uncertainty. They really believe there is, but how does this belief system work? It's probably very different from the mathematical structure we use when we model uncertainty. Another perspective that was quickly mentioned by Jochen yesterday is the perspective of abstraction. So for example, Jochen mentioned yesterday that one way to get around the trap of not being interested by flickering screens and aleatoric uncertainty was to abstract the description of the thing. And when you see this is one flickering screen, this is another one, it's basically all the same at a certain conceptual level. And that's not novel anymore. That's not interesting. And actually, this idea has begun to be relatively systematically explored in a few papers in machine learning. So by groups of people that don't really care modeling what's happening in humans. But basically what they found is that, for example, if you want to build a machine that's exploring an environment that's pretty realistic, like a town like this and various rooms, if you take a classical approach where they are rewarded by forms of novelty that are very perceptual at the level of images or embedding representation of images, they are going to be much less efficient at exploring than if they are equipped, for example, with a linguistic module, which is transforming images in linguistic description, and then they would measure novelty at the linguistic level. And if you do that, for example, here you have on the top, you have two images of beds. From the image perspective, they are very different. From the linguistic perspective, they are nearly the same. And here you can easily see that maybe that's more interesting once you've seen this to explore things like this rather than this. So there are many examples showing up around. Another perspective is that, okay, we've talked a lot about novelty, about uncertainty, about surprise, but there are many other concepts that are around that are potentially important. One is learnability, the other one is empowerment. So just in the previous talk, actually, Daniel explained very well the power of empowerment. That's an approach that's potentially very general, but still it's a different mechanism from novelty and from uncertainty. And another thing is the idea of learnability. So, for example, if you talk about uncertainty and you make the difference between aleatoric uncertainty and epistemic uncertainty, you say, okay, so what's interesting for the brain, or what should be interesting for the brain, is epistemic uncertainty. But in the real world, because the brain has biases, because the world can be changing, it's not always the case that because there is epistemic uncertainty in a certain particular situation, that it's actually possible to reduce it. In many cases, it's actually impossible. You cannot learn any things about that thing. And so that's why what's very important for the brain in many complicated situations is actually to experiment with the situation and to check in practice whether the epistemic uncertainty is reducible. And then it leads an organism to be able to distinguish between situations where maybe there is structure and maybe some other powerful brain could learn from it, but I don't, from a situation where there is epistemic uncertainty, and if I put effort and time in it, I will actually manage to make progress in learning and improving my prediction and my control over these situations. And by the way, what's interesting is that if you explore the world by trying to maximize what we call learning progress, it will automatically generate a curriculum where an organism will explore progressively more complicated situations, problems, goals, while avoiding the ones which are too easy and the ones which are too complicating, which is very similar to many theories of intermediate difficulty or intermediate challenge in psychology, like the theory of flow. But the difference is that you never have to define why it's intermediate. You don't have threshold. You just maximize learning progress. And actually, with Jacqueline, in the last few years, we developed a few experimental paradigms in which human subjects were free to explore various tasks where they could learn various things. And we wanted to model whether their exploration pattern can be explained by utility function that use learning progress as a component. And we actually found very convincing evidence that learning progress is a very important component to take into account to explain their exploratory behavior. And then, just to conclude, when we discuss in the neuroscience and psychology communities about, and also in the machine learning community about curiosity, many people think of it as mechanisms that assign a measure of interestingness to data or to states that can be observed, whether it is novelty, surprise, or progress in predicting what's going to be the next steps. But they assign interestingness to data and to states. This is one family of mechanisms of exploration. There is another very important family of exploration that was actually talked and explained very well by Todd Gurekis in his talk, which is what in the team we like to call autotelic exploration. And so that's the idea that when humans explore the world, and in particular children, they very often organize their exploration by imagining for themselves new goals, new problems, new games. And this is something that's happening at a higher level of abstraction than the other kind of exploration mechanisms. So for example, these children here, they are not so much here putting little pieces of wood and each time like waiting whether to see what's going to happen and waiting to be surprised. No, rather at the beginning they say, oh, what if we would build a very high tower? And they go for it. And that's also the case for much abstract play scenarios. So these children, maybe they say, let's play, we are aviators and we don't have a plane, but let's take a suitcase and we're going to do it. And actually, this kind of mechanism of exploration is something that has now been explored a lot in AI. In the last 6-7 years, there is a whole series of experiments that were made with video games, with robots. Actually, the little photo at the beginning I showed with robots was actually an experiment using autotelic exploration algorithms. And this is a family of exploration that goes like this. You have first a mechanism that's representing a space of goals. Maybe this space is evolving, maybe it learns based on new observation, and it has a mechanism to sample goals based on measure of interestingness. So here actually you can use things like learning progress, but that's defined in a different way. That's progress in controlling certain kinds of goals. Then there is time allocated for pursuing that goal, and then there is self-generation of a score to evaluate whether there is progress toward that goal. And then there are, based on the data collected, it's reused to improve the internal models and the internal knowledge, often using hindsight learning, which is very often goals are not really successful, the ones that are targeted, but by actually doing stuff in the world. For example, imagine a robot, he wants to move this object on the right, he makes a movement, he misses. But after he sees the trajectory he has just built, he has just produced, he can, in hindsight, says, maybe I failed pushing it on the right, but if my goal would have been to push it on the left, then I just succeeded. And so it can always more or less relabel the trajectory and the behavior it has produced by imagining a label that's describing the goals that it is actually fulfilling. And that's a very, very powerful mechanism to learn very efficiently in the world. So now there are many papers showing this is very efficient, but there are many open questions, both in AI, in psychology, and neuroscience. So how are self-generated goals represented? There are many ways to represent goals. So for example, are they representing in terms of mental images, in terms of language, in terms of programs like Todd was suggesting before? How are they selecting and ordered? So here, the measure of interestingness does not apply to data and to states. It applies to the internal definition of goals. And then to conclude, a very open question also is how can we build experimental protocols to study this form of exploration in humans, in children? There are a few trials. We've seen some posters during the week that make steps in that direction. For example, the poster of Yunhui Xu and Laura Schultz, but a lot needs to be done. So I will stop here. And maybe this points to the idea that there is not one curiosity, but many forms of curiosity. Thank you.
Okay, sorry. So this is this is a big deluge. I hope you got it all. Okay, so now, all right. So it's your turn. Let's open the floor. We have half an hour or so, maybe more. And so here we put up just to keep this in your mind, but whatever. So yes, raise your hand and let's ask some questions.
So I don't think it's one of the topics here, but so we talked a lot about motives for exploration, curiosity, which is very optimistic type of thinking, and I really like that. But it seems that many behavioral problems in the real world is a result of lack of exploration, lack of curiosity. And I wondered, what do you think whether the study of the motives for exploration can be used maybe to solve some behavioral problems and for the other side, like can it be helpful in some way?
Does somebody want to answer? Rob.
Sorry, I don't know if I can speak to a ton of that, but we do have a project going where we're looking at trying to use curiosity or boost curiosity of teachers in the classroom as a way of like getting them to try new things and improve quality of teaching in the classroom. So I think, yeah, this sort of lack of curiosity or trying to intervene to get people to be curious is potentially interesting. The way we're doing it, I mean, I'm not doing it. It's these sort of education professionals, is sort of getting people in these interactive sessions, trying to sort of show them examples of trying, new teaching techniques or different teaching techniques from Japan, right? Where there's a very different style of teaching. And, this is an ongoing, like, not clinical trial, right? But an intervention study. I don't have no results to talk about, but we're trying to do that. And I think, it could be interesting more generally, right? And potentially for treatment as well. And maybe, I don't know, folks who are more into the clinical psychology side, maybe this is something that's important for therapy, right? Like getting people to be curious about themselves and curious about other things. And actually one of the other point, on the last one of these, we had Perry Zern talk, who is a political philosopher, among, I think, a bunch of other things. But he was talking about, being curious about different political systems, right? And different solutions to political problems. And, maybe there's a way out of some of the polarization we have, right? Like today. So yeah, I think kind of interesting.
So, yeah. So I'll speak to the question too. So, at least from the neurobiological and circuits perspective, I think that the data indicates that there are different drives and supported by different circuits that sort of underlie this sort of constellation that some people call curiosity. It's novelty. We've heard a lot about many other things, uncertainty reduction, certainly. Because this is handled by different circuits, they're not all necessarily correlated at the level of human beings. And when we do computational psychiatry studies, we can in fact see this kind of decoupling. Patients with OCD, for example, show a very particular uncertainty intolerance, which leads them to check and try to reduce information, but their novelty preferences aren't necessarily predicted by this. So because of that, I think there's a lot of opportunity as we understand more about the circuits to actually begin to modulate in untreatable disorders of mood.
One thing that your question kind of made me think about is a little bit in the context of the clinical literature, but is
Okay.
okay. Thanks. I'll hold it closer. but is also getting at like the causal relationship. I mean, the way that I've always thought about the relationship between curiosity and explorative behavior is you need to be curious in order to act and explore, right? But maybe it's not necessarily that direction, or maybe it's a bidirectional process. And one thing in the clinical literature, I'm not a clinical psychologist, but there is a therapy called behavioral activation therapy, which is based on like literally bringing people out of their own comfort zone and forcing them to explore. And I wonder if that then may work because it's changing people's propensity to be curious, right? Oh, okay.
No, so the depression literature does show that the behavioral activation component of the treatment is the one of the most efficient ones. This, so I studied some learned helplessness, and this is something that take people out of the learned helplessness. So I really agree with you that this is.
I think the failure modes are actually very interesting to learn about how it works. And I really liked the example we had about the misjudged epistemic uncertainty. So you think there is structure, but there is none, because obviously I would say there is an evolutionary advantage to actually see even smallest chances of a structure that could be there. Imagine, for example, throwing a stone and hitting an animal from distance at speed. That is something that's very difficult to do. You can practice it if you know that it can be reliably actually done, but usually it may have not succeeded in the beginning. So it was an evolutionary advantage to be persistent and developing that. But of course, if you go to a roulette table and you think by a pure concentration, you can actually discover how to control the ball, that's total nonsense. And I think the problem is this, the question is, when do we get misled? What are the criteria that may us actually be triggered to be curious about things that actually are nonsense? I mean, it's superstition. I discussed with several people. I'm really fascinated by the question, when do you get superstitious? And I do think one reason one can be triggered in such topics is because we prefer certainty to, even if it's complex, we are ready to pay a price for complexity as long as we can say, okay, it's less uncertain, it's not random, it's controllable.
Yeah, and yeah. Oh yes, I'm sorry, I forgot. Yes, yes.
Yeah, just I think that's super cool. And just throwing out more stuff that I know does exist in like the world of positive psychology and like relationships research. I definitely know there are at least a few people who have tried to intervene, for example, in like relationship stuff. They're like, they tell couples to like go do new things, and they can either do them separately or like they have to do this like game where they like crawl around and do some playful thing, and this like increases relationship satisfaction and all this stuff. And I know in like happiness research, they just like, yeah, interventions that just tell them to increase novelty end up being really positive for a lot of things. I think there's some stuff on like communication also, like in like polarization, as someone said. I think people are like looking into ways to like make people more like giving them learning goals as opposed to like convince the other person you're right goals. These things are also sometimes hard to manipulate, but people are trying to do that to work on decreasing polarization. So I think, yeah, there's cool work in sort of more real world human-y domains.
Is it okay if I switch gears a little bit to a different question, or does someone else have something specific to? Okay. I was thinking I might try to pose like at least part of an answer to one of your questions about definitions. The simple one of like, you know, so for creativity, there's this definition that's often put out there that you've got something that's novel and original, plus also useful, right? I'll just kind of set that aside. But then the one I wanted to mention more about is complexity. And I think that you know, you mentioned, you know, when we think about uncertainty, there's the question of objective uncertainty, but then subjective uncertainty might get you a lot farther. And I think that regardless of what definition you might come up with with complexity, and in aesthetics, people have thought a lot about over the years about how you would define the complexity of a particular image or of a particular type of thing. And, you know, generally they come down with some combination of order and variety and how you might you know, quantify that more specifically. But then I think that as a field, there's been a strong recognition that you're limited in how far you're going to get with any objective measure of complexity. You really need to start thinking about the subjective measure of complexity. And the problem with that is that, of course, in order to do that, you need a world model. You need a model you need to understand the person's, an individual's world model, because something is only learnable, something is only subjectively complex if it is in its relationship to my existing world knowledge, right? And so you know, I don't know. In general, my sense is that often in behavioral economics, that, you know, you want to come up with a general model first before you have to dive into an individual person model. But I think that in this case, you really have to push in the direction of individual person models.
So do you mind if is this working? Yeah. So that's really interesting, and I think that's exactly what this Oprea paper is trying to get at. Is it's literally saying, I have no idea what is complex. So what I'm going to do is I've got these algorithms. I'm going to ask you to do them, and then I'm going to ask you, how much will you pay me if I let you stop doing this algorithm? So it's taking a purely subjective approach, which sounds like it might link into what's been done in these other fields. I think one of the things that I think is useful is that if we can then combine that with some sort of framework, right? So we could just, I mean, one answer to the question is literally, I'm just going to go to every new circumstance and I'm going to elicit this willingness to pay and therefore your subjective complexity, and that's my model of complexity. It's just whatever I measured in this case. But that lacks a certain generalizability. So I was wondering if there's a useful approach might be to combine this sort of subjective thing with a framework to say, oh, well, here's what might be complex, and now it seems that this dimension is really important, this dimension is less important, something like that.
Can I say that, right? Because you're really bringing the topic of costs. So I think I'm speaking. So willingness to pay is a big deal. So if I understood your question correctly, why aren't people more curious than they are? And the answer is that it's hard. Learning is difficult. There are costs, right? So, you know, your mother says, your teacher says, pay attention. And I have a student there who said, come on, you don't mean that literally. And I said, yes, I mean that literally. Your mother is right. Attention is not a value. Attention is a cost. And right, in terms of time and in terms of cognitive effort. And I think one huge scotoma that we have in our field is that we don't understand what are the cognitive costs of mental operations. We don't understand, like, if you need to fixate on something longer, how aversive is that? How costly is that and that will differ by individual. How costly is it to add two numbers versus read a poem? How costly are so many mental operations? And so, I mean, I really think, I know Konstantin thinks about that. I mean, I think that we really need to start thinking seriously, because otherwise we're not going to understand these questions of why people do or do not engage. The other costs may be in anxiety or in, you know, social costs. Maybe I'm going to fail. Maybe I'm going to make an error. Maybe I don't like uncertainty. Maybe I don't even like to engage with questions, right? There are all kinds of different costs, and have to start looking at them.
So there's so many questions up there on this slide. And one thing we haven't been talking about here that I find extremely helpful is this idea that's often attributed to David Marr of these 3 levels of description. So at the computational level, I think many of the questions, especially the ones by the economists, can be really structured beautifully in the sense that, well, if you have some behavior, it's just your job to come up with a model that makes it look rational, because otherwise, well, your model is not capturing what people are doing. So for example, the example what we had before, right? It was, okay, maybe they're superstitious. Well, there are good reasons to be superstitious. It makes it rational if you have the assumption that what you learn will help you later, right? So have the belief that what I'm learning about the rewards helps me, right? And you can also accommodate stuff like learned helplessness in this kind of a framework. And then what Pierre-Yves was talking about, if you go to the level of representations, it becomes super messy immediately, because do I represent my goals in terms of reward functions or these abstract goals? Well, you'll have to implement very different algorithms to do the planning there or looking for the rewards. And then you look at implementational. Fortunately, I don't have to deal with that level of complexity and messiness, but many here in the room are working on that. So I think this structuring about the 3 levels of description is extremely helpful, because the computational level tells you, okay, what's the next experiment I should do? So maybe I do repeated tasks. And if I do repeated tasks, I could have maybe 2 conditions. And one, well, there's lots of structure across the tasks. So shouldn't I have more superstitious in the subjects that do the repeated tasks that are related versus the ones that are not related? So that could be maybe something helpful to address some of these questions.
Hi, I guess I'm going to suggest another question to add to this really nice and beautiful list. So I really like the move that Jacqueline talked about, moving from focusing on world-driven curiosities to sort of internally driven motivations. But just as I think we need a model of the world, we also have models of ourselves, and that can be really important for this kind of self-directed explorations. And I wonder about maybe metacognition as a missing piece to all of these puzzles. And I think there's some hints in some of the talks and posters that talk about the importance of our sense, like our own models of our reasoning processes or our uncertainties, or even our interests and our abilities. And I'm just curious if anyone in this audience works on that or knows about that and how it relates to some of the topics we've talked about the last 3 days.
Anybody an expert on metacognition?
Well, maybe I can actually make a comment about that, and to link with the previous question on intervention to foster curiosity and education. I actually we happen to work on educational project where the aim is to train a muscle of curiosity in children, if I can say. And one of the approach we are taking is actually to first stimulate metacognition. And for example, in the classroom, there are many obstacles for children to express curiosity. There are some social obstacles that are related, like if you're curious and then you're the friend of the teacher, and that's bad. But there are other obstacles which are actually metacognitive and well documented, in the sense that, for example, if you ask children to ask whatever question they might be curious about a text, one of the obstacles is they are not aware of what they don't know, they are not aware of what they don't understand about the text. And so what we've began to do is actually to have them do exercises to become more aware and more conscious of what they don't know. And some of the results we have are very encouraging, in a sense that after those exercises, they are put in a situation where they have opportunities to explore, and they actually explore more. That's a very small result, but that's one step in this direction. I completely agree that metacognition is very tightly linked with curiosity, yes.
Yeah, and that's why you need a bigger meeting, so we can have a section on metacognition.
Hello, hi, can everyone hear me? Hey, I'm Mark Ho. Yeah, I think the question of metacognition is really interesting and important as well. And I haven't done a ton of work on like metacognition per se, but I actually think there's a lot of like ideas from like social cognition that could be kind of brought over to studying metacognitive processes. So like things like theory of mind are in many ways kind of involve kind of a form of metacognition of other people's thought processes. And so in some of the work that I've been involved in, we've kind of like taken some of these like ideas about theory of mind and kind of applied them to like thinking about hierarchical decision making. So like when you're kind of like deciding, how to divide up a task into simpler tasks to solve it, for example, like that can kind of be thought of as like almost like a multi-agent problem, where you're kind of like, you're breaking up, you're kind of like, oh, how am I going to distribute this big problem into a bunch of small problems that these other agents, myself in the future, can solve. So I actually think there's a lot of like potential, very productive directions kind of bridging these ideas, like between kind of social theory of mind, multi-agent systems, and attention, metacognition, these types of things.
Yeah.
Hi, this is not so much to do with metacognition, it's like changing tactics a little bit. Starting to think a bit more about animals, because I think so much cool stuff has been looking about moving like the curiosity research forward in humans and thinking about how to conceptualize it differently. And the task that Ilya sort of described, this non-instrumental information seeking task where animals choose between two things and they get this information, has been used a lot to look at curiosity in animals, right? But I guess you could argue it doesn't really reflect curiosity because, like so many people have been saying, curiosity is so much more than just wanting to know about whether or not you're going to get food in 10 seconds. So my question is kind of, what do people think is next for in animals, right? So some stuff about in humans has been talked about, doing like caller questions and things like that, but with animals it's more difficult. And one thing that strikes me is these learning progress algorithms and maybe trying to see whether animals have this type of thing. Just be interesting to get other people's thoughts on that.
Yeah. Yeah, so I mean, I've been thinking a lot about this. I'm a mouse person, so also in the animal world. And I guess one of the things I've thought a lot about is if we can ask whether animals have a general preference for learnability and predictability, and then look at how that might be rewarding and driving their behavior and choices. Because I think a lot of us feel like, you know, it's hard to make progress in terms of dumping an animal in a box and asking what they're doing because you have no idea why they're doing it. But asking about maybe, you know, predictable world and unpredictable world, and what do they like and why do they like it?
Yeah, well, so we had a similar idea that we got somewhat burned on, but maybe we can make lemonade out of it. So yeah, so we tried to do this, to teach monkeys two lists of to order. So one list had a true order where A was better than B and B was better than C, and another list had a random order. And the idea was to see if they prefer to engage, to get to a stage where we give them a choice. Do they want to engage with the one that I can learn versus one that is unlearnable? But on the way to it, we discovered that when the monkeys got the random list, they impose an order on it. So they started choosing as if that had an order. And they persisted in that order, like superstitious learning, but model-based. It was a transitive inference kind of, they persisted with it even if we penalized them in terms of reward rates. So we don't know, right? What is a random environment to an animal, right? Anyway, but yeah.
Just to sort of build on that, you know, in some cases, I think you can relate task difficulty to learnability. In some, and we proved in one case sort of directly, right? And yeah, that may be another way, and maybe that's what's going on. They think you know, it's more difficult, right? And it's more engaging up to a point, except when, you know, until it gets too difficult. Yeah, maybe another way of seeing.
I mean, there's another approach that I've seen where rats, I think rats are learning something, and then their reaction times are higher at the beginning of the session, higher as if they while they learn and then they decline. There are a lot of questions there, but I think one of the controls that they did is that if at the beginning of the session they get random images that don't convey information, then you don't see this pattern. Right? So this sounds too simple now, but so I'd want to build up on that. So if you have like, right? So right.
Yeah,
Anyway.
I'll briefly comment on that as well. I think it's really important to just remember, at least, you know, our perspective is that curiosity is really a constellation of different drives. And so from the circuit perspective, I think there's just a lot of different questions. Uncertainty reduction is certainly one of them. Novelty is another one, and learnability may be another. And if you think about it sort of from a very bottom-up perspective, what you actually just, at the level of detection, never mind acting, what you need, what kind of algorithm you need to detect a novel stimulus versus the kind that you need to maybe at least try to measure a total uncertainty signal and attribute from that, like what a surprise is from. Is it due to epistemic or just due to noise, for example? These are just very different computations, and I think these computations are underlied by different circuits. So I think it's not a matter of sort of saying, do one paradigm to study curiosity versus another. It's a matter of breaking down curiosity into a more low-level, understandable, computationally tractable family of behaviors that are quantifiable using econometric or whatever methods, and then going into the mechanism. That's at least my perspective.
Yeah. All right. Pietro, you've been
So going back to humans, because this version of animals,
It's okay.
I was thinking, so there is something about curiosity that I haven't seen discussed much, which is the difficulty of the task, both as an element that may stop you from entertaining it, and as an element that may induce you to entertain it. I mean, very few of us would attempt to learn incredibly complicated languages, but very few of us try to learn incredibly simple languages that are very close to ours, right? We often go to the middle ground. But why do we go to why is the challenge part of the fun? I mean, isn't curiosity connected to fun, but fun connected to challenge? It's not just exploration, right? So there's a difference between curiosity about facts, which is sure, but also, for example, curiosity about facts. Why are facts fun? Also because I try to guess them beforehand, and then I'm challenging myself, right? Would I be able to guess that "Hey Jude" was the answer to this morning question about the Beatles? So I think there's something that has to do with the difficulty of the task. So curiosity, which is directed towards solving a task, which must have a difficulty which seems to be optimal when it's intermediate. It's solvable, not easily. And that's a part that I haven't seen discussed much. And I just wanted to bring it up.
Is there evidence that that's optimal for machine learning, Rob?
So you can, yeah, for if you assume gradient descent learning and you assume 2 alternative forced choice, and you assume the only thing I can do is change the difficulty of the task as the experimenter. If I set the difficulty to keep it at 85% correct, I'll maximize the average gradient of a stochastic gradient descent. So the idea is if it's too hard, I make errors all the time, and so I'm making too many errors.
But that has to do with feedback.
Yes. So this is the case of a feedback learning.
I'm thinking about
right?
fun. I think about the utility bonus I get from the process.
Right. So then that would be, this is a machine learning algorithm, right? Very abstract. The idea would be, if you put that into, what's guiding that, right? So if I can just track my accuracy, then if in this task, 85%, I'm learning fastest, right? And so maybe that's rewarding, right? More generally, so Pierre-Yves, I don't know where he's gone. It's sort of this learning progress, right? Similar idea. If I can somehow track my learning progress, I'm doing better. Somehow that's rewarding or engaging, right? But yeah, there's a long way from this abstract thing to the psychological constructs you're talking about, right? But yeah, one thought.
I have a short comment on that. I mean, if you have a domain and the domain is well understood and you want to learn inside the domain, you won't get much information. If you go totally outside of the domain, you have to rebuild completely your structures from scratch, and you don't get much for that because you don't learn the context. So the most you learn when you expand your domain is at the boundary. And in fact, that I speak now through my head, but I would say this is where you get the most information at the given cost. In fact, you could also consider this is the place where you have most influence of what you could learn and you don't learn. And so you could even interpret it in views of empowerment with respect to feedback. So this is the feedback that's most empowered. I don't know, I haven't thought it through, but you could actually interpret it in various ways, this maximum gradient.
So,
Hi.
Is it okay? I have a very different question, if that's okay.
Oh, okay.
I just want to follow up on this quickly.
Follow up on this,
So this is all, I mean, it's slightly in a different direction, but it's inspired by this point, and I think connects to Ilya's and some others. I think to Jackie's point about humility, I think there's a potential worry about creep in terms of curiosity and how we're using that. And when we get to this question of, for instance, kind of what leads us to engage in certain kinds of tasks that are more difficult than others. So there is this question, I think you both point this out about potential for outcomes and learning. But there's also, I think what you're getting at is part, as you said, the process, the kind of experience of effort and other kinds of rewards along the way. And I guess the question I'll kind of lay out is, do we want to call that curiosity? Do we want to kind of include that under the umbrella? There's other reasons you might enjoy the experience of effort. We've written a little bit about this. But I wonder if we want to talk about setting the bounds around what we want to call information seeking and curiosity versus other forms of approach behavior.
I don't know. I mean, I think that effort is a big part and intrinsically motivated. So you asked about fun, right? So I suppose what we would say, fun arises from some sort of intrinsic reward or intrinsic monitoring process, and that is built in a way that it generates a good state that you seek at the point when you learn something, right? And these are all very approximate. So like Mark said, I don't think we calculate information value optimally in any sense, even in the simplest situation where somebody could calculate it into 20 seconds. People don't actually calculate it. So I actually think that information seeking is a sort of emotion. That's why curiosity is an emotion. There's some sort of emotional state that includes a mix of arousal and motivation and approach behavior. And I think we're often confused about that, right? So if something makes us feel good, I think we probably feel that we're learning, even though we're probably not learning, right? So the emotions are very dirty concepts, they're very approximate. So anyway, yeah, that would be my thought.
Yeah, it's a very different question, but it actually turns out to be related to something Daniel brought up in an earlier comment. So something that comes up often in these discussions is exploit paradigm, and that naturally brings one to chasing uncertainty rather than shying away from it in an effort to taper that uncertainty. And one historic way that we do that, which is at least 3,000 years old, is or one way we express that is gambling, right? And I've been thinking about a gambler who says that what they're trying to do is question aleatoric uncertainty and taper it down to become, epistemic uncertainty that they can resolve. And then, obviously we might think that's not the case, but I'm just wondering what are healthy and unhealthy ways to be curious. It's related to this, stemming from the gambling metaphor. So.
Yeah, I'll just say one comment that's really related to this. So in ongoing work with Ethan Bromberg-Martin and Young Fang here, they wanted to actually measure the relationship of risk attitude and information preference. And the experiment started with me telling them that they would be totally correlated, and that was going to be across species and within subject and so on. And it turns out that risk preferences are not correlated to information preferences. So we've separated the data into risk seekers and risk avoiders, and that does not seem to predict the actual subjective value they assign to uncertainty reduction. So this was a big surprise. So I thought I'd share it because it's related to your comment.
Yeah, I think in the animal psychology literature, people have tried to relate information seeking to gambling. Basically, one suggestion is that if it's driven rather than uncertainty reduction, but by overvaluing good news, that same mechanism that motivates people to pick the informative option in some of these psychological tasks also may be what drives people basically to gamble. So some people have interpreted animal behavior in these instrumental seeking tasks actually perhaps as reflecting human gambling behavior. So some people have started to make that link, I guess.
Yeah. So I know that you have posted that I didn't get to on learning trap. I was wondering, is Todd here, or maybe or someone from his lab who can talk about learning traps? Because I was so one thing I was thinking is that information has this really peculiar quantity, which is it's not like a food that you eat and then the drive goes away, right? It satisfies, it goes to zero. I mean, I think information actually expands infinitely. It has this fractal quantity to it, right? So you can I mean, even in the visual domain, I mean, think about it. I can, in this little square of the floor, there's enough information to keep me busy for the rest of my life, because I can focus on it, I can see the average, but then I can start talking about every single pixel, and then within a pixel, and then so on and so forth, right? Until I get to the limit of my receptors, right? And so even things like uncertainty reduction, if you think about a huge exploration space, you could end up in a trap, and you could be like what I used to think of naively as optimal to not be biased and reduce uncertainty and whatever. But as you learn about something, you create more uncertainty because you increase the precision with which you represent that space. And so you could be reducing uncertainty forever, but be trapped into a tiny portion of your of the space, right? So it's that way in which, yeah, it can be. That's one form of unhealthy exploration. Or another form is if you go to, that's more common, confirmation bias is something you want to hear, and then you're trapped forever, and you gain more and more information, you learn more and more, but it's all consistent with your hypothesis, right? So this is why I think this form of, which is mostly unpleasant to most of us, but hearing people contradict our beliefs and say, no, you're wrong, it's actually super healthy for society. Yeah, someone in the back.
Building on that last point, I was one of the things that was most fascinating to me throughout this conference was sort of the ways in which there's actually sort of this sort of tension between these sort of more rational curiosity drives, seeking information, etc., but also all these like self-protective drives, which are sort of like, we want to not lose hope. We want to like maintain our mental health. We want to like not be contradicted or something. And I think I've been, at least coming from the AI perspective, trying to think about like what that means in this context. Like humans and animals are really weird because we have to survive, but also like learn about the world. I don't know. I don't have a question, but it's just building on that. So.
Do you have a response to that directly?
I was just going to make a comment on it, just
Go for it,
related, but just very quick. I mean, this is something I picked up in the conference, was many talks, right, about the self-regulation, and I think Jess, you know, and especially the sort of mind-wandering session really got at that, right? I don't know if you want to add something, but this idea of it really being like a sort of almost homeostatic process, right, of maintaining my mood, and obviously the implications for mental health there, I think is huge.
Yeah, this is and I think related to these two last questions, one thing I was thinking.
Speak louder.
Sure. One thing I was thinking is, hearing many people's comments is, you know, when you talk about curiosity and creativity, they have this very positive connotation to them. But on the other hand, if they're tendencies that were created by evolution, you'd think, well, they're kind of hitting the average. You know, some people would be not curious enough, but other people would be too curious, and so it would be on average. So why is it we put such a positive weight on them? And I think it may be related to the peculiar situation that humans are in and how our society has been changing. You know, right now we're much more wealthy and safe and free than, you know, humans have been for a long time in history. So maybe we're able to be much more curious, and maybe it's much more beneficial for us to be curious than it has been for humans at, you know, times in the past. And so, you know, I think it makes sense for us to try to figure out how can we boost people's curiosity, because this may be an environment that's great for it, but also it may be the environment that has the most traps of those kinds, and the ones that you're talking about. I'm thinking of, for example, infamously, the most common consequence of people clicking on links on Wikipedia is to continue clicking on links on Wikipedia. And so, you know, maybe we have to be especially alert for those pitfalls as well. So.
I had a comment that was like responding to something like 10 minutes ago now, but it's sort of also in response to the original thing. One of the things that I'm really fascinated by is just like how many different things are there that we're talking about here, which someone mentioned in the presentation. And I really liked the data you talked about, Jackie, of like doing your like factor analysis or whatever it was to like see like, is there one parameter capturing a lot of these things across tasks, and then looking at how it was related to other scales. So I'd love to just, as a field, have more work seeing like, is novelty seeking related to whatever other seeking related to curiosity, and just figuring out how many things there are. And I know you've mentioned actually trying to break it down more to get at the mechanisms and saying they're not all correlated. So it's one way I try to make sense of this a little bit is like saying, maybe we have like some small number of innate primary rewards that are what actually makes things fun, and maybe something like learning progress, competence progress could be like that, maybe novelty also. But I imagine there might be a small number of things there, and then a much larger space of things that are learned or innate cues that we use to seek out those things. So novelty could be a signal that we might be able to make learning progress, and there could be a billion of those signals. Yeah, just trying to make sense of this space, I think, is a future thing for the field that would be cool. Anyone can respond to that if they want.
I hook into one thing that I mentioned in the very last line of my slide, that is some approach by Michael Lachman and colleagues about having, basically considering organisms as vessels of different genetic traits, or basically different genetic lines. And they basically, if we play this game in terms of motivations, we could consider humans as, or any organism, as a vessel of different agents, actually. It's not one agent, it's multiple agents, and they actually compete for the limited resources of our time and our attention and our actions. So you may want to, well, you need to practice for your exam or for your talk, and then you want to also to see this Netflix, and you want actually to have some food. Well, you can have the food and the Netflix together, but other things are competing. And so it ends up being actually a game in which different drives compete against each other. It does not even have to be constructively competing. In fact, maybe that's a role of our, I don't know, our control entity that says, no, we prioritize this and this and this. And when that doesn't work, then we have mental health problems, right? So I could imagine that this can be possibly even split up into different agencies, and maybe that's a good way to try to model it.
Just to add, I think, absolutely great point on like the individual differences and the factor analysis, right? I think one thing that we've really got to get in there, and we've seen it in a lot of talks, is the naturalistic tasks and the realistic tasks, and a range of those, right? We've seen spatial and gaze and maybe, turning things, but there's got to be a huge range of like different, exploration tasks or curiosity tasks well, not even tasks, right? Or behaviors in the real world. And do the same factors that we get out of, Jackie's factor analysis map onto these real world things? I think huge question.
Yeah, so I wanted to say about these naturalistic tasks, it's just so exciting to see them. So before, like tasks like you're doing and like Catherine showed, I was just thinking that for all these years until now, there was one study, Risco et al. I don't know if you see it. And what they did is they had people look at pictures, and they looked at the spatial distribution of fixations. And that was already in there. It's totally simple-minded, like a two-figure, two-table paper. Basically, people with higher trait curiosity just had more widespread fixations, gaze patterns. That's it. And that's all we had. And I'm like, my God, can somebody do something like this? That's more of this. And I'm so happy to see that it's coming up. Yeah. And also, I wonder if you can like extend it to the semantic level. Like instead of, right, this is now all spatial entropy, but if you could somehow partner with Pierre-Yves or somebody and do a conceptual model, and then you look at the conceptual entropy or a semantic level entropy of what people experience, that would be even more powerful.
I mean, Kate was trying to get at that a little bit, right?
Yeah,
I don't know if
exactly. She was, with a demographic measure, right. And another question that I have is if anybody did linguistic analysis of questions, what kind of questions people ask, right? It seems that there wouldn't be that many type of questions. There would be, why, how, who, where, when, something like that. Like, it seems like you should be able to classify the questions and then classify people by how many questions they ask. I know because I ask a ton of questions, so much. Yeah, I cannot talk to my son early in the morning. I have to give him 2 hours because, like, Mom, stop asking me questions I don't know. But I'm sure that they're individual, and that would be like the first proxy. I mean, I wonder if, I don't know, I keep asking if such an analysis has been done. It seems like it should be. What? Yeah? Yeah?
Yeah, I guess I can. Yeah, I have this task where I present participants with statements that have like gaps kind of in them and then ask them to generate questions. And so we do see like when people generate questions, they're more curious, and then that their questions, if they're more, they'll search for the information that's more semantically relevant to the questions that they asked. So, yeah.
But it's more about generate.
Yeah, I mean, well, they can be connected to like the gaps we've kind of placed in the statement. But yeah, is that kind of what you're looking for? Okay, okay, okay.
Or something like you have your ongoing narrative. I would say.
Yeah.
I really don't have much to say about this, but a student did start coding it, trying Quentin, putting it in the sort of information framework. It's one thing to think, but it's another thing to think in a way where you're mulling over information. You're getting the instrumentality of that topic that you're considering, right? So one way to go about that, at least he thought of, is kind of code for questions, code for what if,
right.
I wonder, et cetera.
Right, exactly. And I wonder if that can be, so the gap, so what we said in this info seeking task, we capture uncertainty directed versus random. And you, in more realistic tasks, you capture something else that's more closely related to the personality trait. But maybe is the number of questions that is a bridge. So maybe the number of questions in semantic output tells you something about uncertainty attitudes, you know?
Related to your question about semantic space and roaming entropy, there's one study by Leiden Staley in Nature Human Behavior. And I think there are other studies that use Wikipedia and basically show how the way people search Wikipedia pages, whether they go very broad, diverse, like reflect in diversive curiosity, versus more going deep, related to more deprivation sensitivity. So I think that's the closest I can think of, where people look at that more in semantic space and how people explore semantic space.
That's true, right.
And maybe a short comment, Jacqueline, also on this topic. So we've been actually also using a few existing coding systems for questions when we in educational projects where we try to foster curiosity and question asking in children, and that's tough. That's tough. What we found is that very often questions generated by children break the coding system. Like they invent questions that we didn't think of, that are out of the grid, and we don't know what to do with it. And sometimes they are nice, they are curious, but not in the sense we were expected. And so that's a real, I would say that's a pretty open, there are a few papers on the coding system, but that's an open question to do it solidly.
I see. Can you give an example? Something you can't classify?
Okay, so yes, one example. So we give little text to children, and we give them a little bit of hints to try to generate divergent questions, but still that are related to the topic of the text. And we had a text that was about dinosaurs, like traditional stuff they study in the life sciences in primary schools. And then there was one child who asked the question, is Brigitte Macron a dinosaur? And so where do you put that question? I mean, is it really related to the text? Is it curious? Is it only humor? So for those who don't know, Brigitte Macron is the wife of the French president.
Any more? You have your hand up. You want to? Still relevant? No. Okay. All right. So,
So,
yeah,
so
yeah.
just about your question, whether there's more work linking semantic space and uncertainty. So there's a paper that just came out in Nature Human Behavior from Oriel Feldman Hall's lab, linking intolerance of uncertainty to the similarity of like semantic representations in a semantic space, basically showing that people who are more intolerant to uncertainty basically push apart their representations more in their semantic network. So that was just in the newest issue. So just in case
Okay,
you
thank
missed
you.
that, I
Yeah,
find that interesting.
super relevant. Thanks. I'll look it up. Okay, well, we're a little bit over time, so this is fun. Thank you all again for coming, and I hope we continue it not too far future. Thank you.